we are deep diving into everything we need to know about the edge of the universe. This matters because it represents the ultimate boundary of everything we can ever know, see, or interact with. It is not just a physical limit, but a fundamental constraint on human knowledge itself. Unlike the edge of a forest or the shore of an ocean, the edge of the observable universe is a boundary created by the finite speed of light meeting the expansion of space itself. This edge tells us something profound about the nature of reality, about time, about causation, and about the very possibility of information transfer across the cosmos. When we contemplate the edge of the universe, we are really asking questions about the limits of existence, the shape of space-time, and whether anything can truly be said to exist if it can never, even in principle, affect us or be observed by us. The edge of the universe is not where space ends. This is perhaps the most important and least understood aspect of cosmic boundaries. When astronomers and physicists talk about the edge of the universe, they are almost always referring to the edge of the observable universe, which is a sphere centered on Earth with a radius of about 46 billion light-years in every direction. This edge exists not because space stops there, but because light from beyond that distance has not had enough time to reach us since the beginning of the universe. The universe itself, the actual totality of all that exists, may well be infinite in extent. It might go on forever in all directions, with galaxies and stars and planets beyond counting, stretching away into an endless expanse that no human will ever see or measure or confirm. What makes the edge of the observable universe so fascinating is that it is constantly moving. Every second that passes, light that was previously too far away to have reached us completes its journey across the cosmos and arrives at our telescopes. This means the observable universe is always growing, always encompassing more space, more galaxies, more of the actual universe. However, this growth is not straightforward because space itself is expanding. The expansion of space means that distant objects are moving away from us, and the farther away they are, the faster they recede. At a certain distance, objects are receding from us faster than the speed of light. This does not violate Einstein's special relativity, because the objects themselves are not moving through space faster than light. Rather, the space between us and those objects is expanding, carrying them away from us. The cosmic event horizon is perhaps one of the most philosophically troubling concepts in modern cosmology. This horizon represents the boundary beyond which events happening right now will never be observable to us, no matter how long we wait. Because the expansion of the universe is accelerating, driven by the mysterious dark energy that makes up about 68% of the universe's total energy content. There are galaxies that are currently visible to us that we will never be able to visit or communicate with, even if we could travel at the speed of light. The light from these galaxies is reaching us now, but any signal we sent toward them would never arrive, because the space between us is expanding too quickly. In a very real sense, these galaxies are already lost to us, slipping past a point of no return, falling beyond the edge of what we can ever interact with. This creates a strange situation where the universe we can observe is larger than the universe we can causally interact with. We can see galaxies whose light left them billions of years ago, and that light is reaching us now. But if we tried to send a message to where those galaxies are now, accounting for their motion due to the expansion of space, that message would never reach them. The expansion would carry them away faster than our signal could travel. This means there is a sphere around us, smaller than the observable universe, that represents the limits of our possible causal influence. Anything beyond this sphere is forever beyond our reach no matter what technology we develop or how long we wait. The particle horizon is another crucial boundary in cosmological thinking. This is the distance that light has been able to travel since the beginning of the universe. If the universe is 13.8 billion years old, you might think the particle horizon would be 13.8 billion light-years away. However, because space has been expanding during all that time, the objects that emitted the light we see from the earliest moments of the universe have been carried much farther away. They are now about 46 billion light-years distant. This is why the radius of the observable universe is 46 billion light-years, rather than 13.8 billion light-years. The light has been traveling for 13.8 billion years, but the source of that light has been moving away from us the entire time. When we look at very distant galaxies, we are looking backward in time. A galaxy that is 10 billion light-years away is seen as it was 10 billion years ago because the light we are observing left that galaxy 10 billion years ago and has been traveling through space ever since. This means that as we look out toward the edge of the observable universe, we are looking back toward the beginning of time itself. The farthest objects we can observe are seen as they were when the universe was very young, just a few 100 million years after the Big Bang. We cannot see anything from before, about 380,000 years after the Big Bang, because before that time, the universe was opaque. It was so hot and dense that light could not travel freely through it. Instead, photons were constantly scattered by free electrons in a dense plasma that filled all of space. The cosmic microwave background radiation is the oldest light we can observe. It comes from the moment when the universe cooled enough for atoms to form, allowing light to travel freely for the first time. This happened about 380,000 years after the Big Bang, and the light from this event has been traveling through space ever since, cooling and redshifting as the universe expands. Today, this ancient light appears as microwave radiation coming from every direction in the sky. It forms a sort of wall at the edge of the observable universe, a surface of last scattering beyond which we cannot see with electromagnetic radiation. This surface is not a physical barrier, but a temporal one. We cannot see beyond it because there was no free light to carry information from earlier times. The concept of inflation adds another layer of complexity to understanding the edge of the universe. Inflation is a theory that proposes the universe underwent an extremely rapid expansion in the first tiny fraction of a second after the Big Bang. During this inflationary period, space expanded exponentially, doubling in size many times over in an incredibly short time. This expansion was much faster than the speed of light, again not violating relativity because it was space itself that was expanding. Inflation explains several puzzling features of the universe, such as why it appears so uniform on large scales, and why space appears to be flat rather than curved. However, inflation also has profound implications for the edge of the universe. If inflation happened, it means the actual universe is vastly larger than the observable universe. The part we can see might be an infinitesimally small fraction of the whole. There might be regions of space so far away that they inflated away from us to distances that place them forever beyond our cosmic horizon. The topology of the universe is another rarely discussed aspect of cosmic boundaries. When we talk about the universe being flat, we mean that the geometry of space on large scales follows Euclidean geometry, where parallel lines never meet, and the angles of a triangle add up to 180 degrees. However, flatness does not necessarily mean the universe is infinite. It is possible for space to be flat but finite if it has an unusual topology. For example, space could be shaped like a three-dimensional torus, where if you travel far enough in one direction, you eventually return to where you started, similar to how video game characters disappearing off one side of the screen reappear on the other side. In such a universe, there would be no edge at all. You could travel in any direction forever and never reach a boundary because space would curve back on itself. Current observations suggest that if the universe does have such a topology, it must be much larger than the observable universe, so we would not notice the wrapping around. The possibility of a multiverse adds yet another dimension to questions about the edge of the universe. Some versions of inflation theory suggest that inflation never completely ends everywhere at once. Instead, inflation stops in some regions, creating bubble universes like ours, while continuing in other regions. Each bubble universe would have its own observable universe edge, its own physical laws potentially, and its own history. These bubble universes would be separated from each other by regions of space that are still inflating. If this is true, then our universe, the totality of everything that exists, might itself be just one region within a much larger multiverse. The edge of our bubble universe would be fundamentally different from the edge of our observable universe. It would be a true boundary, where the properties of space and time might change, where physical constants might have different values, where the laws of physics as we know them might not apply. String theory and its variants suggest even more exotic possibilities for what might lie beyond the edges we can observe. In string theory, space has more than 3 dimensions. The extra dimensions are curled up so small that we cannot perceive them directly, but they influence the behavior of particles and forces in our 3-dimensional space. Some versions of string theory propose that our entire universe is a 3-dimensional membrane, or brane, floating in a higher dimensional space called the bulk. Other branes might exist in this bulk, representing other universes with which we could potentially interact gravitationally, but not through any other force. In such scenarios, the edge of our universe might be a boundary in these higher dimensions, a place where our brane ends and the bulk continues, or where our brane meets another. The holographic principle is one of the most mind-bending ideas to emerge from theoretical physics in recent decades, and it has profound implications for understanding cosmic boundaries. The holographic principle suggests that all the information contained within a region of space can be encoded on the boundary of that region, like a hologram that stores 3-dimensional information on a 2-dimensional surface. Applied to the entire observable universe, this principle suggests that everything we see, all the galaxies and stars and planets, all the matter and energy and information, might be encoded on a distant 2-dimensional surface at the edge of the observable universe. In this view, the 3-dimensional universe we experience might be a kind of projection or hologram of information stored on this distant boundary. This idea comes from studies of black holes, which have an event horizon that acts as a boundary beyond which nothing can escape. The entropy of a black hole, a measure of the information it contains, is proportional to the area of its event horizon rather than its volume. This surprising result led physicists to wonder if the same principle might apply to the universe as a whole. The far future evolution of the universe has significant implications for how we think about its edge. Current observations suggest the expansion of the universe is accelerating, driven by dark energy. If this acceleration continues, as most cosmologists expect, the universe will undergo what is sometimes called the Big Rip, the Big Freeze, or the Heat Death, depending on the specific behavior of dark energy. In the most likely scenario, known as the Big Freeze or Heat Death, the universe will continue expanding forever, becoming increasingly cold, dark and empty. Galaxies outside our local group will recede beyond the cosmic event horizon, disappearing from view one by one. Eventually, even the stars within our own galaxy will burn out, leaving only black dwarfs, neutron stars, and black holes. On even longer timescales, these remnants will decay or evaporate, leaving nothing but a thin soup of elementary particles in an ever-expanding space. In this far future, the observable universe will become much smaller than it is today, because the accelerating expansion will push more and more of the cosmos beyond the cosmic event horizon. Our distant descendants, if any exist, will live in an island of matter surrounded by an ever-growing void, with no evidence that anything exists beyond their local group of galaxies. The measurement of the edge of the observable universe involves some of the most sophisticated instruments and techniques in all of science. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope can observe galaxies formed when the universe was just a few 100 million years old. Radio telescopes detect the cosmic microwave background radiation, mapping its tiny temperature variations to learn about the structure of the early universe. These observations allow cosmologists to measure fundamental properties of the universe, such as its age, its expansion rate, and its composition. The expansion rate, known as the Hubble constant, is one of the most important numbers in cosmology, but it has proven surprisingly difficult to measure precisely. Different methods of measuring the Hubble constant give slightly different results, a discrepancy known as the Hubble tension. And this tension suggests we might be missing something important about how the universe works. The cosmic web is the large-scale structure of the universe, a vast network of galaxy clusters, filaments, and voids that extends to the edge of the observable universe. Galaxies are not distributed randomly through space but are organized into this web-like pattern, with dense filaments and clusters separated by vast, mostly empty voids. This structure formed over billions of years as gravity pulled matter together, amplifying tiny density variations that existed in the early universe. Observations of this cosmic web extend our knowledge nearly to the edge of the observable universe, giving us a view of how matter is distributed on the largest possible scales. The web is not static, but constantly evolving as galaxies move under the influence of gravity and the expansion of space. Understanding this structure helps cosmologists test their theories about how the universe formed and evolved. Dark matter plays a crucial role in shaping the universe on large scales, including near the edge of what we can observe. Dark matter is a mysterious substance that does not emit, absorb, or reflect light, making it invisible to telescopes. However, it exerts gravitational influence on visible matter, and astronomers can infer its presence by observing how galaxies move and how light bends around massive objects. Dark matter makes up about 27% of the universe's total energy content, far more than the ordinary matter that makes up stars, planets, and people. Without dark matter, galaxies would not have enough mass to hold themselves together, and the cosmic web would look very different. As we observe galaxies near the edge of the observable universe, we are also observing the effects of dark matter on those distant structures, giving us clues about the distribution and properties of this enigmatic substance. Dark energy is even more mysterious than dark matter, and plays an even larger role in determining the ultimate fate of the universe and the evolution of its edge. Dark energy makes up about 68% of the universe's total energy content, yet we do not know what it is or why it exists. We know it exists because observations show the expansion of the universe is accelerating. Distant supernovae are farther away than they should be if the universe were expanding at a constant rate, indicating that the expansion has been speeding up over the past few billion years. Dark energy is thought to be a property of space itself, a sort of inherent energy that empty space possesses. As the universe expands and more space is created, more dark energy comes into existence, driving the acceleration of the expansion. This acceleration has profound implications for the edge of the universe because it determines how the cosmic event horizon evolves over time and which parts of the universe will remain observable in the far future. The anthropic principle is sometimes invoked when discussing why the universe has the properties it does, including properties that affect the nature of its edge. The anthropic principle states that we observe the universe to have properties compatible with the existence of intelligent observers, because if it had different properties, we would not be here to observe it. This principle can be weak or strong. The weak anthropic principle is simply the observation that any universe we observe must be capable of supporting observers. The strong anthropic principle suggests that the universe must have properties that allow observers to evolve. Some cosmologists use anthropic reasoning to explain why certain physical constants have the values they do. For example, if the strength of dark energy were much larger, the universe would have expanded too quickly for galaxies and stars to form, and we would not exist. If dark energy were much smaller, or attractive rather than repulsive, the universe might have recollapsed in a big crunch long ago. The universe we observe appears to be finely tuned for the existence of complex structures like galaxies, stars, and planets, and some physicists argue this is evidence for a multiverse where different bubble universes have different physical properties, and we necessarily find ourselves in one compatible with our existence. The maximum size the observable universe can ever reach is finite, even though it continues to grow. This might seem contradictory, but it follows from the accelerating expansion driven by dark energy. As space expands faster and faster, light from distant objects becomes increasingly redshifted, stretched to longer and longer wavelengths. Eventually, this redshift becomes so extreme that the light carries effectively no energy and cannot be detected. Additionally, objects beyond the cosmic event horizon are receding from us so quickly that light they emit now will never reach us. This combination of factors means there is a maximum distance we can ever observe, a maximum number of galaxies we can ever see, even if we wait forever and have perfect instruments. Current estimates suggest the observable universe will grow by only a factor of 2 or 3 from its current size, before dark energy pushes everything else beyond the event horizon, leaving our local group of galaxies isolated in an ever-expanding dark void. The concept of the cosmological horizon draws an interesting parallel with the event horizon of a black hole. Just as nothing can escape from beyond a black hole's event horizon, no information can reach us from beyond our cosmological horizon. Both horizons represent fundamental limits on what can be observed or interacted with. Some physicists have explored the mathematical similarities between these two types of horizons, finding deep connections between the physics of black holes and the physics of cosmology. These connections suggest that both phenomena might be understood as different manifestations of the same underlying principles about how information is stored and processed in space-time. The fact that both types of horizons have a temperature and entropy associated with them, despite one being incredibly small and the other encompassing the entire observable universe, hints at a deep unity in the laws of physics operating at all scales. The end of cosmic inflation marked a critical moment in the early universe that set the stage for the formation of the observable universe and its edge. When inflation ended, the enormous energy driving the exponential expansion of space, was converted into matter and radiation, heating the universe to incredibly high temperatures. This moment is sometimes called reheating. The matter and radiation created during reheating eventually cooled and evolved into the galaxies, stars, and planets we see today. The end of inflation did not happen everywhere at the same instant. Quantum fluctuations during inflation meant some regions stopped inflating slightly earlier or later than others. These tiny variations in the timing of inflation's end created small differences in the density of matter in different regions. And these density differences were the seeds that eventually grew into the cosmic web of galaxy clusters and voids. The edge of the region where inflation ended defines a kind of boundary to our universe, though this boundary is far beyond what we can observe. The curvature of space is intimately connected to questions about the edge of the universe. Einstein's general theory of relativity tells us that mass and energy curve space-time, and this curvature determines how objects move through space and how light travels. On small scales, near stars and planets, this curvature is noticeable as what we call gravity. On the largest scales, the average curvature of the entire universe determines whether space is positively curved, like the surface of a sphere, negatively curved, like a saddle, or flat, like an infinite plane. Current observations indicate the universe is flat or very close to flat on large scales. A flat universe can be infinite in extent, stretching on forever in all directions with no edge. A positively curved universe is finite, but has no edge, curving back on itself like the surface of a sphere. A negatively curved universe can be infinite and has a saddle-like geometry. The flatness of the universe is itself something of a mystery, because for space to be as flat as observations indicate, certain properties of the early universe had to be fine-tuned to incredible precision. Inflation provides a natural explanation for this flatness by expanding space so much that any initial curvature was stretched out to undetectable levels. Quantum mechanics introduces additional complications when thinking about the edge of the universe and what might lie beyond. At the quantum level, particles can exist in superpositions of states, being in multiple places or having multiple properties simultaneously until measured. Some interpretations of quantum mechanics, particularly the many worlds interpretation, suggest that every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome. If this interpretation is correct, then there might be an enormous number of parallel universes, each representing different sequences of quantum outcomes. These parallel universes would not be separate regions of space, but rather different branches of reality existing in a sort of superspace. The edge of our universe in this view would not be a boundary in physical space, but a boundary between different branches of the quantum multiverse. The arrow of time is closely related to the expansion of the universe, and thus to the concept of its edge. Time's arrow refers to the fact that time appears to have a direction. Events happen in a particular sequence. We remember the past but not the future. Entropy, a measure of disorder, increases over time. All these aspects of time's arrow can be traced back to the fact that the universe started in a highly ordered, low-entropy state at the Big Bang, and has been evolving toward higher entropy ever since. The expansion of the universe is intimately connected with this increase in entropy. As space expands, the matter and energy in the universe spread out and become more disordered. In the far future, when the universe has expanded enormously and all the stars have burned out, entropy will have increased to near its maximum possible value, and the universe will be in a state of maximum disorder. The edge of the observable universe constantly receding as space expands, is in a sense the frontier where this process of increasing entropy is occurring. As more and more space comes into being, and the universe moves further from its ordered beginnings. The concept of causality is fundamentally connected to cosmic horizons. Causality is the principle that cause must precede effect, and that all effects must have causes. In physics, causality is intimately linked with the speed of light, which represents the maximum speed at which information or influence can travel. The cosmic event horizon represents the boundary of causally connected space, the region within which events can, in principle, influence each other. Beyond this horizon, causality breaks down in a practical sense. Events occurring beyond the horizon cannot causally affect us, and we cannot causally affect them. This raises profound philosophical questions about the nature of existence and reality. If there are regions of the universe that can never interact with us, even in principle, in what sense can we say they exist? Is existence something that requires the possibility of observation or interaction? Or can something exist in a completely isolated, unobservable state? The observable universe is sometimes compared to an island of knowledge, surrounded by an ocean of the unknown. This metaphor is apt because it captures both the finite extent of what we can know and the vast, perhaps infinite, expanse of what lies beyond. Like inhabitants of an island who can see only to the horizon, we can observe only the portion of the universe from which light has had time to reach us. Unlike islanders, however, we cannot simply build a boat and sail beyond our horizon to see what lies there. The horizon of the observable universe is not just limited by our current technology or location, but by the fundamental physics of space-time and the finite speed of light. No matter how long we wait or how good our instruments become, there are regions of space we will never be able to observe because they are receding from us faster than light can travel to bridge the gap. The heat death of the universe is the ultimate fate predicted for a universe with accelerating expansion driven by dark energy. In this scenario, the universe will continue expanding forever, becoming increasingly cold, dark, and dilute. Stars will burn out, black holes will evaporate through Hawking radiation, and eventually even protons may decay, leaving only a thin gas of photons, neutrinos, and other lightweight particles. As this process continues, the universe will approach a state of maximum entropy, where all energy is evenly distributed and no work can be done. In this far future, the observable universe will be much smaller than today, containing only the remnants of our local group of galaxies, everything else having receded beyond the cosmic event horizon. The edge of the observable universe will have contracted in a sense, not because space stops expanding, but because the accelerating expansion pushes everything else beyond where we can see. The role of time in defining the edge of the observable universe cannot be overstated. The edge exists because time is finite into the past. The universe has a finite age, and light has had only a finite time to travel, so there is a maximum distance from which light can have reached us. If the universe were infinitely old, and if space were not expanding, light from arbitrarily distant objects would have had time to reach us, and there would be no observable universe edge. The finite age of the universe, combined with the finite speed of light, creates the boundary we observe. This boundary is constantly moving outward as more time passes and light from more distant sources reaches us. In this sense, the edge of the observable universe is a time horizon as much as a space horizon, marking not the end of space, but the limit of how far back in time we can see. Moving now to the more familiar aspects of cosmic boundaries, we can discuss how telescopes and other instruments allow us to probe these distant realms. Every advance in telescope technology has pushed the edge of the observable universe further away, revealing more distant and ancient galaxies. Early telescopes could see only nearby stars. Modern telescopes can see galaxies billions of light years away, appearing as they were billions of years ago. The Hubble Space Telescope revolutionized our understanding of the distant universe, capturing images of galaxies in the deep field observations that showed thousands of galaxies in regions of sky that appeared empty to ground-based telescopes. The James Webb Space Telescope, with its larger mirror and infrared capabilities, can see even further, detecting light from the first galaxies that formed in the universe. These observations bring us closer to the edge of the observable universe, closer to the moment of the Big Bang, and give us a more complete picture of cosmic history. Redshift is the key to measuring distances to faraway galaxies and understanding the expansion of the universe. When light travels through expanding space, its wavelength is stretched, shifting it toward the red end of the spectrum. The amount of redshift tells astronomers how much the universe has expanded since the light was emitted, which in turn tells them how far away the object is and how long ago the light was emitted. The most distant galaxies observed have redshift so large that their light, originally emitted as visible or ultraviolet light, has been stretched all the way to infrared wavelengths. These high redshift galaxies are seen as they were more than 13 billion years ago, when the universe was just a few 100 million years old. Observing these distant, ancient galaxies gives astronomers a window into the early universe, showing what galaxies looked like when they were first forming, and how the universe has changed over cosmic time. The Big Bang itself is not an explosion in space, but an expansion of space. This is a crucial distinction that helps clarify what is meant by the edge of the universe. The Big Bang did not happen at a particular location in space. It happened everywhere simultaneously. Every point in space was once concentrated together in an incredibly hot, dense state, and all of space has been expanding ever since. This means there is no center of the universe and no edge in the traditional sense. Every observer, no matter where they are located, sees themselves at the center of their own observable universe, surrounded by a spherical region from which light has had time to reach them. An observer in a distant galaxy would see a different observable universe, centered on their location, overlapping partly with ours, but extending into regions we cannot see. The formation of the first stars and galaxies is one of the most active areas of research in cosmology, particularly as it relates to observations near the edge of the observable universe. After the Big Bang and the subsequent period, when the universe was filled with opaque plasma, there was a time called the Cosmic Dark Ages, when the universe was dark, filled with neutral hydrogen gas, but no stars. The first stars formed a few 100 million years after the Big Bang, when gravity pulled together dense clumps of this hydrogen gas, until they became hot enough to ignite nuclear fusion. These first stars were likely much more massive than typical stars today, burning hot and bright and living fast, short lives before exploding as supernovae. The ultraviolet light from these first stars ionized the surrounding hydrogen gas, beginning a process called reionization that eventually made the entire universe transparent again. The first galaxies formed shortly after, as gravity pulled together large collections of stars, gas, and dark matter. Observing these first stars and galaxies, which exist near the edge of our observable universe, helps astronomers understand how the universe transitioned from the simple, uniform state seen in the cosmic microwave background to the complex, structured universe we see today. As we approach the conclusion of this exploration, it becomes clear that the edge of the universe represents far more than a simple boundary. It embodies the limits of human knowledge, the constraints imposed by physical law, and the profound questions that arise when we push our understanding to its ultimate frontiers. The edge reminds us that we live in a universe governed by finite speeds, by causes and effects, by the relentless expansion of space itself, and by the invisible influence of dark matter and dark energy. Understanding the edge of the universe has required humanity's greatest intellectual achievements, from Einstein's theories of relativity to quantum mechanics, to the latest observations from space telescopes. This understanding continues to evolve as new discoveries reveal unexpected features of the cosmos, and as theoretical physics explores ever more exotic possibilities for what might lie beyond what we can see. The edge of the observable universe is not a wall or a barrier, but a horizon, beyond which lies mystery, perhaps infinite space, perhaps other universes, perhaps realities so strange we can barely imagine them. Just as exploring beyond one horizon often reveals another horizon further distant, understanding the edge of our observable universe opens up new questions, new horizons of knowledge to explore, leading us to wonder about the nature of existence itself, the origins of physical laws, and the ultimate fate of everything that is. This brings us to consider what lies beyond our current understanding, beyond even the theoretical frameworks we have constructed, into realms where physics, philosophy, and imagination converge to explore the deepest questions about reality and existence. When we ask what we actually mean by the edge of the universe, we are really asking multiple questions disguised as one. The word edge itself carries assumptions that may not apply to the cosmos. An edge typically implies a boundary between something and nothing, a place where one thing ends and another begins, like the edge of a table or the edge of a cliff. But the universe does not have an edge in this familiar sense. There is no place where space stops and nothingness begins, no cosmic cliff over which one could fall, no barrier marking the end of existence. Instead, when cosmologists speak of edges, they are referring to horizons, boundaries not of space itself, but of observation, of causality, of time. These horizons are multiple and distinct, each with its own meaning and implications, and much of the confusion surrounding the edge of the universe stems from failing to distinguish between them. The particle horizon is perhaps the most fundamental type of edge we can discuss. It represents the maximum distance that light could have traveled since the beginning of the universe. If the universe is 13.8 billion years old, then light has had 13.8 billion years to travel. But due to the expansion of space during that time, the sources of the light we see from the earliest moments are now much farther away than 13.8 billion light-years. They are approximately 46 billion light-years distant. The particle horizon is thus a sphere centered on us, with a radius of about 46 billion light-years. Beyond this horizon lie regions from which light has not yet had time to reach us. These regions may contain galaxies, stars, and planets, but we cannot see them because their light is still in transit. The particle horizon is constantly expanding as more time passes, and light from more distant sources completes its journey to us. In this sense, the edge defined by the particle horizon is not fixed, but moves outward at a rate determined by the speed of light and the expansion of space. The event horizon is a different type of edge entirely, one that is more permanent and more philosophically troubling. While the particle horizon marks the boundary of what we can currently observe, the event horizon marks the boundary of what we can ever observe, even if we wait forever. In a universe with accelerating expansion driven by dark energy, There are regions of space that are receding from us so quickly that light emitted from those regions now will never reach us. The space between us and those regions is expanding faster than light can cross it. These regions lie beyond our event horizon. What makes the event horizon particularly significant is that it represents a true and permanent loss. Galaxies that slip beyond our event horizon are gone forever, not just from our view, but from any possible interaction. We cannot send signals to them, we cannot visit them, we cannot affect them in any way. They are causally disconnected from us for all eternity. The event horizon is actually shrinking in certain respects, because the accelerating expansion is pushing more and more of the universe beyond this boundary, isolating our local region of space from an ever-growing portion of the cosmos. The Hubble sphere is yet another type of boundary, one defined by the expansion rate of the universe. The Hubble sphere is the distance at which the recession velocity of space equals the speed of light. Objects at the Hubble distance are neither approaching nor receding from us in terms of the light they emit reaching us. Objects closer than the Hubble distance are receding slower than light speed, so light they emit can make progress toward us, even though space is expanding. Objects farther than the Hubble distance are receding faster than light speed, so light they emit is actually carried farther away from us initially, though if the expansion rate changes or slows, that light might eventually turn around and make progress toward us. The Hubble sphere is important because it marks a transition in how we think about the observability of distant objects. The radius of the Hubble sphere is approximately 14 billion light-years, smaller than the particle horizon, but not identical to the event horizon. Objects beyond the Hubble sphere but inside the event horizon are currently receding faster than light, but we can still see them because they were closer than the Hubble sphere in the past when they emitted the light we now observe. The cosmological horizon combines aspects of both the particle horizon and the event horizon, representing the ultimate boundary of the observable universe, taking into account both past and future. In a universe with accelerating expansion, the cosmological horizon is finite and represents the maximum comoving distance from which light can ever reach us. Comoving distance is a way of measuring distance that factors out the expansion of space, essentially asking how far away something would be if we could freeze the expansion right now. The cosmological horizon in our universe is approximately 16 billion light-years in co-moving distance, though this translates to a much larger distance when we account for the expansion that has occurred. This horizon is shrinking in co-moving coordinates as the accelerating expansion of space pushes more regions beyond the boundary from which light can reach us. The distinction between coordinate systems is crucial for understanding what we mean by distance, and therefore what we mean by an edge. In cosmology, there are several ways to define distance, and they do not all agree. Proper distance is the distance you would measure if you could freeze the expansion of the universe and lay rulers end to end between 2 points. Comoving distance factors out the expansion, measuring distance in coordinates that expand with space. Light travel distance is the distance light has traveled to reach us, which is smaller than the proper distance because space has been expanding during the light's journey. Angular diameter distance relates to how large an object appears in the sky. Luminosity distance relates to how bright an object appears compared to its intrinsic brightness. Each of these distance measures can give different values for the same object, and each implies a different meaning for how far away the edge is. When cosmologists say the observable universe has a radius of 46 billion light-years, they are using comoving distance. The proper distance to the edge is larger still, because space has continued to expand while light was traveling to us. The misconception that the universe must have an edge if it has a finite age is one of the most common errors in thinking about cosmology. This misconception assumes that a universe with a beginning must be finite in size, like a balloon that started small and expanded. However, infinity is a strange thing. An infinite universe can have a beginning in time without having an edge in space. Imagine an infinite line of numbers extending in both directions. Now imagine compressing that line so all the numbers are closer together, then letting it expand back out. The line was always infinite, but its density changed over time. Similarly, the universe could have always been infinite in spatial extent, but started in an infinitely dense state that has been expanding and becoming less dense ever since. In such a universe, there would never be an edge, no matter how far you traveled or how long you waited. Every point in this infinite space would have its own observable universe surrounding it, a finite sphere from which light has had time to arrive. But beyond each observable universe would lie more space, more galaxies, more of the infinite whole. The flatness of space has direct implications for whether the universe has an edge. Current observations indicate that space is flat, or very close to flat on large scales, meaning that Euclidean geometry applies. Parallel lines never meet. The angles of a triangle add up to 180 degrees, and space does not curve back on itself. In a flat universe, space can be infinite, extending forever in all directions with no edge. However, flatness does not require infinity. Space could be flat but finite if it has an unusual topology, wrapping around on itself like a video game screen, where exiting on one side brings you back on the opposite side. In such a universe, you could travel in a straight line forever and never reach an edge, but you would eventually return to your starting point. Current observations suggest that if the universe does wrap around, it does so on scales much larger than the observable universe, so we would not notice the periodic boundary conditions within the region we can observe. The concept of nothing is intimately connected to questions about the edge of the universe. When people imagine an edge, they often imagine space ending and nothing existing beyond. But what could it mean for nothing to exist? Nothing is not a thing, not a substance or a void or empty space. Nothing is the absence of everything, including space itself. It is meaningless to ask what lies beyond the edge of space, because beyond implies a spatial relationship, and if there is no space, there can be no beyond. This linguistic and conceptual confusion has plagued discussions of cosmic boundaries for centuries. Even the phrase "the universe" suggests a single, bounded entity. But if the universe is everything that exists, then by definition, there can be nothing outside it, no beyond, no elsewhere. The universe is not a thing in space. It is space itself, along with all the matter and energy it contains. The history of human thinking about cosmic boundaries reveals how our conceptions of edges have evolved. Ancient cosmologies often featured literal edges, boundaries where the known world ended and chaos or void began. The ancient Greeks debated whether space was finite or infinite, with Aristotle arguing for a finite cosmos bounded by the sphere of fixed stars, and atomists like Democritus arguing for infinite space filled with infinite worlds. Medieval cosmology placed Earth at the center of a series of nested spheres carrying the planets and stars, with the outermost sphere marking the edge of creation. The scientific revolution shattered this finite cosmos, revealing that Earth orbits the Sun, that stars are distant suns, and that space extends vastly farther than anyone had imagined. Yet even as telescopes revealed ever more distant objects, the question remained whether space was finite or infinite, whether it had an edge or extended forever. The development of general relativity transformed the question of cosmic boundaries by showing that space itself is dynamic, capable of expanding, contracting, and curving. Einstein's equations revealed that the universe could not be static, but must be either expanding or contracting. Initially, Einstein was so convinced the universe must be static that he added a cosmological constant to his equations to balance gravity and prevent collapse. When Edwin Hubble discovered that distant galaxies are receding from us with velocities proportional to their distance, indicating the universe is expanding, Einstein reportedly called his cosmological constant his greatest blunder. Yet ironically, modern observations have shown that a cosmological constant, or something like it, dark energy, really does exist and is causing the expansion to accelerate. This history shows how our understanding of edges and boundaries has been repeatedly overturned by observation and theory. The observable universe is often called a bubble or sphere, but these terms can be misleading. They suggest a three-dimensional object with a two-dimensional surface, like a soap bubble in air. But the observable universe is not like this. It is not a bubble floating in some larger space. Rather, it is a region of space-time defined by light cones, the past light cone of here and now, extending back to the Big Bang. Every point in the universe has its own past light cone, its own observable universe. These observable universes overlap extensively, but they are not identical. An observer in a distant galaxy sees a different observable universe, one that overlaps with ours in the middle, but extends into regions we cannot see, while missing regions near us that lie beyond their horizon. There is no preferred center, no absolute edge, only relative horizons depending on one's location, and the time elapsed since the Big Bang. The surface of last scattering is a specific and important boundary, a spherical shell surrounding us from which the cosmic microwave background radiation originates. This surface represents the moment, about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this recombination, the universe was opaque, filled with a plasma in which photons were constantly scattered by free electrons. After recombination, photons could travel freely through space, and the universe became transparent. The cosmic microwave background consists of these ancient photons that have been traveling through space for over 13 billion years, cooling and redshifting as the universe expands. We cannot see beyond the surface of last scattering using electromagnetic radiation, because before recombination, the universe was opaque. This surface is a true horizon, not just for our current telescopes, but for any telescope based on detecting light. It is as close as we can come to observing the actual moment of the Big Bang using photons. Gravitational waves and neutrinos offer the possibility of peering beyond the surface of last scattering. Unlike photons, neutrinos interact very weakly with matter and were able to travel freely through the early universe, even before recombination. If we could detect the cosmic neutrino background, the bath of neutrinos left over from the early universe, we could in principle observe events from when the universe was just 1 second old. Similarly, gravitational waves, ripples in space-time itself, travel unimpeded through matter and could carry information from even earlier times, potentially from the inflationary epoch in the first fraction of a second after the Big Bang. These observations would not change the edge of the observable universe as defined by the particle horizon, but they would push back the observational horizon to earlier and earlier times, revealing more about the universe's first moments. The difference between can we see it now and will we ever be able to see it is subtle, but crucial. There are galaxies that we cannot see now, because their light has not yet reached us, but we will be able to see them in the future as their light continues its journey across expanding space. These galaxies are beyond our current particle horizon, but will eventually enter the observable universe. However, because the expansion of the universe is accelerating, there are also galaxies we can see now that we will not be able to see in the far future. The acceleration is pushing these galaxies beyond our event horizon, and eventually their light will be redshifted to infinitely long wavelengths, becoming undetectable. Over trillions of years, more and more galaxies will disappear from view as they cross the event horizon, leaving our local group increasingly isolated. The edge of the observable universe defined by the particle horizon will continue to grow, but the edge defined by which galaxies we can actually observe will shrink. The cosmological principle is a foundational assumption in modern cosmology, stating that on large scales, the universe is homogeneous and isotropic. Homogeneous means the same everywhere, and isotropic means the same in all directions. This principle implies that there is no special location in the universe, no center, and no edge that would make one region fundamentally different from another. Every observer, regardless of where they are located, should see essentially the same large-scale structure, the same average density of galaxies, the same cosmic microwave background, the same expansion rate. The cosmological principle is supported by observations showing that the universe looks remarkably uniform, on scales larger than a few 100 million light-years. If the universe has an edge in the sense of a boundary, where conditions change, this would violate the cosmological principle. Therefore, most cosmologists believe the universe either extends infinitely with no edge, or wraps around on itself with no boundary. The horizon problem was one of the major puzzles that led to the development of inflationary cosmology. The cosmic microwave background radiation is incredibly uniform, with temperature variations of only about 1 part in 100,000 across the sky. This uniformity suggests that different regions of the early universe were in thermal equilibrium at the same temperature. However, according to standard Big Bang cosmology without inflation, regions on opposite sides of the sky would never have been in causal contact. They lie beyond each other's particle horizons, meaning light would not have had time to travel between them since the Big Bang. How, then, could they have come to the same temperature? Inflation solves this problem by proposing that all the regions we can now observe were once much closer together, in causal contact, before inflation expanded them to vast distances. During inflation, a tiny region smaller than an atom expanded to become larger than the observable universe, preserving the uniformity established in that tiny initial region. The quantum origin of cosmic structure provides another perspective on edges and horizons. The galaxies, galaxy clusters, and cosmic web we observe today all originated from tiny quantum fluctuations in the very early universe. During inflation, quantum uncertainty at microscopic scales was stretched to cosmic scales, creating regions of slightly higher and lower density. After inflation ended, these density differences grew under gravity, eventually forming the large-scale structure we see today. The observable universe preserves a record of quantum fluctuations that occurred on scales smaller than the horizon during inflation. The edge of the observable universe thus corresponds roughly to the edge of the region that was within a single horizon volume during the inflationary epoch. Beyond our observable universe lie other regions that originated from different quantum fluctuations, regions we can never observe because they are beyond our particle horizon. The role of dark matter in defining observable boundaries is significant because dark matter makes up most of the matter in the universe, and dominates the gravitational dynamics that create structure. Dark matter does not emit light, so we cannot observe it directly, but we can infer its presence from its gravitational effects on visible matter and light. The distribution of dark matter extends to the edge of the observable universe and beyond, creating a gravitational scaffolding on which galaxies and galaxy clusters form. Near the edge of the observable universe, we see young galaxies forming within dark matter halos, the gravitational wells created by concentrations of dark matter. These observations help us understand how structure formation proceeded in the early universe, but they also remind us that most of the universe is invisible, composed of dark matter and dark energy that we detect only through their effects. The anthropic selection effect complicates discussions of what we mean by the edge of the universe. The anthropic principle observes that we can only observe a universe capable of producing observers. If the universe were much smaller or much younger, galaxies and stars might not have had time to form, and intelligent life might not exist. The size of the observable universe is related to its age through the speed of light, and its age is related to the processes that create heavy elements and planets. We necessarily find ourselves in a universe old enough and large enough for life to arise. This observation does not tell us whether the universe is finite or infinite, but it does suggest that any intelligent observers will find themselves in a universe with an observable region of roughly similar size to ours, regardless of the actual total size of the universe. The edge as a product of perspective is perhaps the most important insight in understanding what we mean by cosmic boundaries. The edge is not an objective feature of the universe itself, but a consequence of our particular location in space and time. The observable universe is observer-dependent. Different observers see different observable universes. An alien astronomer in a galaxy 10 billion light-years away sees a different observable universe than we do, one that overlaps with ours, but extends into regions we cannot see, and misses regions near us that are beyond their horizon. In this sense, asking where the edge of the universe is located is like asking where the edge of my visual field is located when I look at a landscape. The edge is not a property of the landscape, but a property of my observation of it, determined by the limits of my vision and my location. Similarly, the edge of the observable universe is not a property of the universe, but a property of our observation of it, determined by the speed of light, the age of the universe, and our location. The distinction between physical and metaphysical edges is worth considering. A physical edge would be a place where the laws of physics change, where space-time itself ends or transitions to something else. Current cosmological theories do not predict such an edge within the observable universe. The laws of physics appear to be the same everywhere we can observe. However, some theories do predict metaphysical edges, boundaries beyond which we cannot make observations or test predictions even in principle. The event horizon is a metaphysical edge in this sense. It marks a boundary beyond which we can say nothing definitive about what exists, because no information from beyond that boundary can ever reach us. We can speculate, we can extrapolate our theories, but we cannot confirm or refute those speculations through observation. This raises philosophical questions about the nature of scientific knowledge and whether it is meaningful to say something exists if it is, by definition, forever unobservable. The mathematical edges in cosmological models are different from physical edges. When cosmologists construct models of the universe, they often work with specific geometries and topologies, mathematical descriptions of how space is shaped and connected. Some of these models have edges or boundaries in a mathematical sense, places where the coordinate system breaks down, or where certain quantities become infinite. However, these mathematical features do not necessarily correspond to physical edges. They might be artifacts of the coordinate system chosen, or they might represent genuine physical singularities, like the Big Bang itself, which is sometimes described as an edge in time rather than space. The Big Bang represents a boundary to the past, a moment before which the classical description of space-time breaks down and quantum effects become dominant. The possibility of cyclic universes introduces another conception of edges. Some cosmological models propose that the universe undergoes cycles of expansion and contraction, with each Big Bang followed eventually by a big crunch, which then rebounds into a new Big Bang. In such models, the Big Bang is not the absolute beginning, but merely the latest in a series of transitions. The edge in time represented by the Big Bang might not be a true edge, but a transition point where the universe passes from one phase to another. These models remain speculative and face significant theoretical challenges, but they illustrate how different conceptions of cosmic boundaries depend on different assumptions about the nature of time and the ultimate fate of the universe. The edges we can never cross are perhaps the most frustrating for creatures like us, who are driven to explore. Even if we could travel at the speed of light, we could never reach most of the galaxies we can see. The expansion of space would carry them away faster than we could approach them. The galaxies we could potentially reach, even in principle, are limited to our local group, a collection of a few dozen galaxies gravitationally bound together. Everything beyond our local group is receding from us and will eventually pass beyond the event horizon, becoming forever unreachable. In the far future, if civilization survives for trillions of years, our descendants will inhabit a universe very different from ours, one in which the only visible galaxies are the merged remnants of the Milky Way and Andromeda, with everything else having disappeared beyond the horizon into darkness. The edge as a limit of knowledge rather than a limit of space is the most accurate way to understand cosmic boundaries. The universe may well be infinite, with no spatial edge, but our knowledge is necessarily finite. We can know only what light and other signals have had time to bring us, only what lies within our past light cone, only what is causally connected to us. This limit is not a failure of our telescopes or our theories, but a fundamental constraint imposed by the structure of space-time and the finite speed at which information can travel. The edge of the observable universe marks the boundary of the knowable, the limit beyond which we pass from empirical science, based on observation, into pure speculation, based on extrapolation. The comfort and discomfort of edges both play roles in how we think about the universe. On one hand, edges are comforting because they define and contain. They give a sense of completeness and comprehensibility. A finite universe that we could, in principle, fully map and understand has a certain appeal. On the other hand, edges are disturbing because they raise the question of what lies beyond. An infinite universe avoids this question by having no beyond, but infinity itself is disturbing, difficult to truly comprehend, implying that no matter how much we discover, there is always infinitely more remaining unknown. Perhaps the actual situation, an infinite universe of which we can observe only a finite portion, combines both the comfort and discomfort, giving us a comprehensible local region to study while preserving the mystery of what lies in the unreachable vastness beyond. In the end, what we mean by the edge of the universe depends entirely on which edge we are discussing: the particle horizon, marks the boundary of what we can currently observe. The event horizon marks the boundary of what we can ever observe. The Hubble sphere marks the distance at which recession velocity equals light speed. The surface of last scattering marks the earliest moment from which we can detect electromagnetic radiation. Each of these boundaries is real, meaningful, and distinct. None of them represents an edge in the simple sense of a place where space stops. They are horizons, limits imposed by the physics of light, time, and expanding space. Understanding these different edges, distinguishing between them, and recognizing what each one means is essential for making sense of cosmological discussions and for appreciating the strange and wonderful nature of the universe we inhabit. As we contemplate these various horizons and boundaries, we begin to see that the question of edges leads naturally to even deeper questions about the fundamental nature of space and time themselves, about whether these familiar concepts remain valid at the extreme scales and conditions that define cosmic boundaries, and what new physics might be needed to fully describe reality at its most fundamental level. What happens at the edge, according to physics, is perhaps the most counterintuitive aspect of cosmic boundaries. Nothing dramatic occurs there. No wall appears. No barrier blocks further travel. No cosmic police officer turns you around. The edge of the observable universe is not a place where anything happens in the traditional sense. It is a horizon, a boundary of observation rather than a physical barrier. And what makes it fascinating is precisely what does not happen there. An observer traveling through the edge would notice nothing special at all. They would pass through seamlessly, unaware they had crossed any boundary, because the edge exists only relative to distant observers, not as an absolute feature of space-time. Yet from our perspective, looking toward that distant horizon, physics predicts a series of increasingly strange phenomena, effects that transform how we see objects approaching the edge and what becomes of the information they carry. The infinite redshift at the cosmic event horizon represents one of the most extreme predictions of cosmological physics. As an object approaches the event horizon, moving away from us in the accelerating expansion of the universe, light emitted by that object becomes increasingly redshifted. Redshift occurs because the wavelength of light is stretched by the expansion of space, shifting the light toward longer wavelengths and lower energies. Near the event horizon, this redshift becomes extreme. Light that was emitted as visible blue light might be stretched to infrared, then to microwave, then to radio wavelengths. As the object crosses the event horizon, the redshift approaches infinity. The wavelength becomes infinitely long, the frequency approaches zero, and the energy carried by each photon becomes vanishingly small. In practical terms, the object fades from view, becoming dimmer and redder until it disappears completely. This is not because the object itself changes or because it hits a barrier, but because the light it emits can no longer bridge the growing gap between the object and us. The asymptotic approach to invisibility is a gradual process rather than a sudden disappearance. An object moving toward the event horizon does not vanish in an instant, but fades slowly, asymptotically approaching invisibility over an infinite time. From our perspective, we would see the object become dimmer and redder, slowing down in apparent motion, appearing to freeze as it approaches the horizon. This freeze is not real in the object's reference frame. The object continues moving normally, crosses the horizon without noticing anything unusual, and proceeds onward into the region of space beyond our causal reach. But from our perspective, the object never quite reaches the horizon. It takes infinite time to appear to cross, becoming infinitely redshifted and infinitely dim. effectively disappearing from the universe as we can observe it. This parallels what happens to objects falling into black holes, where observers far from the black hole see infalling objects appear to freeze at the event horizon, becoming dimmer and redder, never quite crossing over. The thermodynamics of cosmic horizons reveals deep connections between gravity, quantum mechanics, and information theory. Just as black holes have a temperature and entropy associated with their event horizons, cosmic event horizons also possess thermodynamic properties. The temperature of our cosmic event horizon, called the Gibbons-Hawking temperature, is incredibly tiny, far colder than the cosmic microwave background radiation. This temperature arises from quantum effects near the horizon, similar to Hawking radiation from black holes. When quantum fields exist in the presence of a horizon, particle-antiparticle pairs can form near the horizon through quantum fluctuations. If one particle falls beyond the horizon while the other escapes, the escaping particle appears as thermal radiation to distant observers. For cosmic horizons, this effect is extraordinarily weak, producing a thermal radiation with a temperature measured in billionths of a degree above absolute zero. But its existence demonstrates that horizons are not merely geometric features, but physical entities with measurable properties. The entropy of the cosmic horizon is proportional to its surface area, a result that echoes the famous Bekenstein-Hawking entropy formula for black holes. Entropy measures the information content or disorder of a system, and the fact that horizon entropy depends on area rather than volume is profound and puzzling. It suggests that all the information about what lies beyond our cosmic horizon, all the galaxies and stars and particles in that vast volume of space, can somehow be encoded on the two-dimensional surface of the horizon itself. This idea is central to the holographic principle, which proposes that the universe might be fundamentally two-dimensional, with the three-dimensional reality we experience being a kind of holographic projection from information stored on a distant boundary. While speculative, this principle has emerged from serious attempts to reconcile quantum mechanics with gravity and represents one of the most radical proposals in theoretical physics. The no-hair theorem for cosmic horizons suggests that horizons, like black holes, are remarkably simple objects characterized by only a few parameters. A black hole is completely described by its mass, electric charge, and angular momentum, regardless of what fell into it to create it. All other information about the material that formed the black hole is lost behind the event horizon, a property called having no hair. Cosmic horizons exhibit similar simplicity. The cosmic event horizon in our universe is characterized primarily by the radius at which the recession velocity equals the speed of light, which depends on the density of dark energy and the expansion rate of space. The detailed structure of space-time beyond the horizon, the specific arrangement of galaxies and matter, does not affect the properties of the horizon itself. This simplicity suggests deep physical principles at work, principles we do not yet fully understand, but which govern the behavior of all horizons, regardless of their origin. The information paradox at cosmic horizons parallels the famous black hole information paradox. When matter falls into a black hole, it carries information with it, information about its quantum state, its composition, its history. If this information is truly lost behind the event horizon, it would violate quantum mechanics, which holds that information is never destroyed. Similarly, as galaxies and matter slip beyond our cosmic event horizon, they carry information with them into a region we can never access. Is this information truly lost, or is it somehow preserved in a form we cannot detect? The question remains unresolved, But some physicists argue that information falling past a horizon must be encoded on the horizon itself through subtle correlations in the Hawking radiation or other quantum effects. If this is true, then the cosmic event horizon preserves information about everything that crosses it, encoding the history of all the galaxies that have slipped beyond our reach in quantum correlations. Too subtle to observe directly, but present nonetheless. The Unruh effect provides another window into the physics of horizons. The Unruh effect states that an accelerating observer will perceive a thermal bath of particles, even in what appears to be empty space to an inertial observer. The temperature of this thermal bath is proportional to the acceleration. For cosmic horizons, observers at different locations experience different apparent accelerations due to the expansion of space, and these accelerations correspond to different temperatures. An observer near the cosmic event horizon would, in principle, measure a slightly higher temperature than an observer far from the horizon. These effects are extraordinarily small with our cosmic horizon, but they demonstrate that horizons create local thermal environments, that acceleration and horizons are intimately connected through quantum field theory, and that what appears as a vacuum to one observer may appear as a warm bath of particles to another. The causal structure of space-time near the cosmic horizon becomes increasingly complex. Causal structure refers to which events can influence which other events, determined by the light cones that define how information can propagate. Near the cosmic event horizon, the causal structure is distorted by the rapid expansion of space. Light cones tilt and stretch, reflecting how the expansion carries distant objects away faster than light can propagate. An observer near the horizon would find that their ability to influence distant regions, to send signals that will be received, becomes increasingly limited. There exists a boundary beyond which no signal they send can ever reach us, and similarly, no signal we send can ever reach them. This boundary is not fixed in space, but moves dynamically as the expansion continues, creating a complex and time-dependent causal structure that challenges our intuitive understanding of cause and effect. The behavior of test particles near the cosmic horizon depends on their velocities and trajectories. A photon emitted exactly at the cosmic event horizon, aimed directly at us, would make no progress toward us. The expansion of space would carry it away at exactly the speed it tries to approach, leaving it stationary in moving coordinates. A photon emitted just inside the event horizon, aimed at us, would slowly make progress, taking infinite time to cross the shrinking distance as space expands beneath it. A photon emitted just beyond the event horizon would be carried away, its distance from us increasing over time, despite traveling at the speed of light in our direction. For massive particles, the situation is even more complex because they cannot travel at light speed. A spacecraft at the cosmic event horizon would need to travel faster than light relative to local space to make progress toward us, which is impossible. Any spacecraft beyond the horizon is doomed to be carried away from us, regardless of how much fuel it burns or how powerful its engines are. The proper distance to the cosmic horizon increases over time, even though the horizon in co-moving coordinates is shrinking. Proper distance is the distance you would measure if you could freeze the expansion and lay rulers end to end. As space expands, the proper distance to any fixed co-moving coordinate increases. The cosmic event horizon sits at a particular co-moving coordinate, determined by the expansion rate and the properties of dark energy. In co-moving coordinates, this horizon approaches a finite limit as time goes to infinity. But because space is expanding, the proper distance to this co-moving coordinate grows without bound. In other words, the horizon is simultaneously approaching us in co-moving coordinates and receding from us in proper distance. This apparent contradiction resolves when we recognize that different distance measures capture different aspects of the expanding universe, and both are correct within their respective frameworks. The fate of quantum entanglement across the cosmic horizon raises profound questions. Quantum entanglement is a phenomenon where two particles can be correlated in ways that cannot be explained by classical physics, such that measuring one particle instantaneously affects the state of the other, regardless of the distance between them. If two entangled particles are separated and one crosses the cosmic event horizon while the other remains inside, what happens to the entanglement? Standard quantum mechanics says the particles remain entangled, their quantum states still correlated. But the particles can no longer interact causally, and no information about one particle can reach the other. This creates a strange situation where quantum correlations exist across a boundary that forbids any causal connection. Some physicists argue this demonstrates that quantum entanglement is not a mechanism for faster-than-light communication, since the correlations cannot be used to transmit information. Others suggest it reveals limitations in how we understand quantum mechanics in curved and expanding space-time. The equivalence principle suggests that local physics is the same everywhere, regardless of whether you are near a horizon or far from one. An observer crossing the cosmic event horizon would not experience anything unusual. They would not feel any force, see any boundary, or detect any change in the local laws of physics. The space around them would look perfectly normal, with galaxies visible in all directions, though the galaxies they see would be different from those we see. This is because the equivalence principle, a cornerstone of general relativity, states that freely falling observers in a gravitational field experience no local effects of gravity. At the cosmic horizon, an observer is simply moving through space-time, carried by the expansion of space, and locally everything appears normal. The strange effects we observe, the infinite redshift and apparent freezing, are artifacts of our distant perspective, not objective features of the horizon itself. The cosmic censorship hypothesis relates to whether singularities, points where physical quantities become infinite, can be visible or must be hidden behind horizons. In black hole physics, the cosmic censorship hypothesis states that singularities cannot be naked, exposed to outside view, but must be cloaked behind event horizons. An analogous principle might apply to cosmic horizons, suggesting that the most extreme conditions in the universe, regions where space-time curvature becomes infinite, or where classical physics breaks down, are always hidden behind some kind of horizon. The Big Bang singularity, for instance, is hidden behind the particle horizon, shielded from direct observation by the surface of last scattering. If inflation is correct, even earlier moments when quantum effects dominated are hidden behind the horizon established during inflation. This cosmic censorship protects us from observing regions where our theories fail, regions where the fabric of space-time itself might tear or behave in ways we cannot predict. The role of dark energy in creating the cosmic horizon cannot be overstated. Dark energy is the mysterious component that makes up about 68% of the universe's energy content and causes the expansion of space to accelerate. Without dark energy, in a universe dominated only by matter and radiation, the expansion would slow over time due to gravity, and there would be no cosmic event horizon. Every galaxy would eventually become observable, given enough time. But dark energy works against gravity, pushing space to expand faster and faster, creating a situation where distant galaxies are carried beyond our reach. The properties of dark energy, particularly whether it remains constant or changes over time, determine the size and evolution of the cosmic event horizon. If dark energy is truly constant, a cosmological constant, as Einstein originally imagined, then the horizon will stabilize at a particular size. If dark energy changes, the horizon might grow, shrink, or behave in more complex ways. The phantom energy scenario represents an extreme version of dark energy, with disturbing implications for cosmic horizons. Phantom energy is a hypothetical form of dark energy that increases in density as the universe expands, violating the dominant energy condition that normal matter and energy obey. In a universe dominated by phantom energy, the expansion would accelerate without bound, eventually tearing apart not just the fabric of the cosmic web, but galaxies, stars, planets, atoms, and even subatomic particles in a catastrophic end known as the Big Rip. As the Big Rip approaches, the cosmic event horizon would shrink rapidly, not just in moving coordinates but in proper distance as well. More and more of the observable universe would slip beyond the horizon. Galaxies would be torn from their clusters, stars from galaxies, planets from solar systems, until finally, at the moment of the Big Rip, the horizon would shrink to zero, and space-time itself would be torn asunder. Current observations suggest phantom energy is unlikely, but the possibility cannot be completely ruled out. The turnaround point for photons near the cosmic horizon is a fascinating feature of expanding space-time. A photon emitted toward us from just beyond the cosmic event horizon initially moves away from us because the expansion of space carries it away faster than it approaches. However, if the expansion rate is decreasing, or if the photon is not too far beyond the horizon, there can come a time when the photon stops receding and begins approaching. This happens because as the photon moves through space, the local expansion rate it experiences changes. If it moves into a region expanding more slowly, it can eventually turn around and make progress toward us. The turnaround point depends on the detailed dynamics of dark energy and the expansion history of the universe. For photons emitted well beyond the event horizon in our universe, dominated by dark energy that remains constant or increases, no turnaround occurs. These photons recede forever, never to reach us. The observational consequences of horizon physics are subtle, but measurable. The most distant galaxies we observe appear not only distant, but also faint, small, and highly redshifted. Their light has been traveling for over 13 billion years, and during that time, space has expanded enormously, stretching the wavelengths and sapping the energy. Galaxies near our particle horizon have redshifts of 10 or higher, meaning their light has been stretched to more than 10 times its original wavelength. These galaxies are also receding from us at velocities approaching or exceeding the speed of light due to the expansion of space. We see them not as they are now, but as they were more than 13 billion years ago, when they were young, small, and still forming their first stars. What these galaxies look like today, we can never know, because the light showing their current state will never reach us. They have already crossed the event horizon and slipped beyond our grasp. The cosmic no-hair conjecture for horizons suggests that all cosmic horizons settle into a stable, simple configuration over time, regardless of their initial conditions. Just as black holes quickly settle into a state, described by only a few parameters after they form, cosmic horizons might similarly simplify. In our universe, as more and more structure crosses the event horizon and disappears from view, the observable universe becomes increasingly smooth and featureless on large scales. Billions of years in the future, after most galaxies have crossed the event horizon, the observable universe will contain only our local cluster, a small island of matter in an otherwise empty and featureless expanse. The cosmic horizon will be a simple, smooth surface, characterized entirely by its radius and the properties of dark energy, with no memory of all the complex structure that once existed beyond it. The singularity theorems of Penrose and Hawking have implications for cosmic horizons. These theorems demonstrate that under certain reasonable conditions, general relativity predicts the existence of singularities, points where space-time curvature becomes infinite and the classical description of physics breaks down. The Big Bang is such a singularity, and black hole centers contain singularities. Horizons are intimately connected to singularities, often serving as boundaries that hide singularities from outside observation. The cosmic particle horizon hides the Big Bang singularity, while black hole event horizons hide their internal singularities. Some theorists speculate that cosmic event horizons might similarly hide future singularities, regions where space-time becomes so distorted by dark energy that classical physics fails. These speculations remain unconfirmed, but they highlight how horizons and singularities are fundamentally linked in the structure of space-time. The ADS-CFT correspondence, a powerful tool in theoretical physics, provides insights into how physics at boundaries relates to physics in the bulk. This correspondence, developed in string theory, states that a gravitational theory in a space with a boundary is equivalent to a non-gravitational quantum field theory living on that boundary. While this correspondence was developed for anti-de Sitter space, which has different properties from our universe, physicists hope similar principles might apply to cosmic horizons. If so, the physics of the three-dimensional universe we observe might be equivalent to some kind of quantum field theory, living on the two-dimensional surface of the cosmic horizon. This would provide a concrete realization of the holographic principle and could offer new ways to understand how information is preserved as matter crosses horizons. The problem of time in quantum gravity becomes particularly acute when considering horizons. In quantum mechanics, time is an external parameter, a label that tells you when things happen. In general relativity, time is part of space-time, a dynamic entity that can be warped and stretched. Combining quantum mechanics with general relativity requires understanding how to treat time consistently, and this remains one of the deepest unsolved problems in physics. Near horizons, where both quantum effects and strong gravitational fields are important, the problem of time becomes critical. What does it mean to say an event happens at the cosmic horizon? From our perspective, objects take infinite time to reach the horizon. From the object's perspective, crossing takes finite time. Which is correct? Both are correct in their own reference frames, but reconciling these perspectives in a quantum theory of gravity remains a challenge. The firewall paradox, originally proposed for black holes, might also apply to cosmic horizons. The firewall paradox asks what an observer falling through a black hole event horizon would experience. Naive application of quantum mechanics suggests they should encounter a wall of high-energy particles, a firewall, that would incinerate them as they cross. But this contradicts the equivalence principle, which says they should experience nothing unusual. The paradox arises from trying to preserve information in quantum mechanics while respecting the smoothness of the event horizon predicted by general relativity. For cosmic event horizons, a similar paradox might arise. An observer crossing our cosmic event horizon should experience smooth, empty space according to general relativity, but quantum considerations about information preservation might suggest something more dramatic. Most physicists believe the resolution involves a more subtle understanding of quantum entanglement and information flow. But the paradox highlights how much we still do not understand about the quantum nature of horizons. The chronology protection conjecture addresses whether time travel is possible and relates to the structure of horizons. Some solutions to Einstein's equations allow for closed time-like curves, paths through spacetime that loop back on themselves in time, potentially enabling time travel. Horizons often play a role in these solutions, serving as boundaries between normal regions and regions with closed time-like curves. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics conspire to prevent macroscopic time travel, perhaps through quantum effects that become strong near would-be time machines. If this conjecture is correct, it places constraints on what can happen near horizons, ensuring that they remain well-behaved and do not give rise to time travel paradoxes. The cosmic event horizon, being a null surface like the horizons in time machine spacetimes, might be subject to similar protection mechanisms. The gravitational redshift near massive objects provides an everyday example of effects similar to those at cosmic horizons. When light climbs out of a gravitational well, it loses energy and becomes redshifted. This is measurable even for relatively weak fields like Earth's gravity. Near the event horizon of a black hole, gravitational redshift becomes infinite. Light emitted near the horizon reaches distant observers with infinitely long wavelength and zero energy, effectively disappearing. The cosmological redshift at the cosmic event horizon is not gravitational redshift, but rather the stretching of space itself. Yet the mathematical description is similar. Both represent situations where light trying to bridge a gap loses energy to the geometry of space-time, becoming redshifted to the point of invisibility. This parallel suggests deep connections between gravitational physics and cosmological physics, between local curvature created by mass and global expansion driven by dark energy. The future evolution of physics at the cosmic horizon depends on the fate of dark energy. If dark energy remains constant, the horizon will stabilize, approaching a fixed co-moving distance as the universe ages. The physical effects I have described, the infinite redshift, the thermal radiation, the encoding of information on the horizon, will continue indefinitely. If dark energy decays over time, the horizon might recede, allowing some currently unreachable regions to become observable again. If dark energy increases, as in the phantom energy scenario, the horizon will contract, and the universe will march toward a big rip, where even atomic nuclei are torn apart. Observations over the coming decades, measuring the precise behavior of dark energy through surveys of distant supernovae, galaxy clusters, and the cosmic microwave background, will determine which of these futures awaits. For now, the evidence suggests dark energy is constant or nearly so, pointing toward a stable horizon and a heat death rather than a dramatic end. The principle of general covariance states that the laws of physics should be expressible in a form independent of the coordinate system chosen. This principle underlies general relativity and has important implications for horizons. A horizon is a coordinate-dependent concept. In one coordinate system, an event horizon might appear as a special boundary. In another coordinate system, it might not appear special at all. This does not mean horizons are not real, but rather that their properties depend on the observer. The physics at a horizon, what actually happens there, must be described by quantities that are coordinate independent, quantities that all observers agree on. Identifying these invariant features and understanding how they give rise to the observer-dependent phenomena like redshift and apparent freezing remains an active area of research. It requires careful mathematical analysis of how different observers slice space-time into space and time, and how their observations relate to the underlying geometry. The notion of complementarity in quantum mechanics might apply to horizons. Complementarity, introduced by Niels Bohr, states that certain pairs of properties cannot be simultaneously well defined, like position and momentum. For horizons, there might be a complementarity between the description given by an infalling observer who crosses smoothly and the description given by an external observer who sees objects freeze and radiate thermally. Both descriptions might be correct within their domains of applicability, even though they seem contradictory. The infalling observer experiences smooth, empty space, while the external observer sees a hot, radiating surface. These are complementary descriptions, neither more true than the other, each valid in its own context. Accepting this complementarity might be necessary for understanding the full quantum nature of horizons, just as accepting wave-particle duality was necessary for understanding quantum mechanics. The role of quantum fluctuations at the cosmic horizon is subtle but potentially important. In quantum field theory, even the vacuum is not truly empty, but filled with constant fluctuations, virtual particles briefly popping in and out of existence. Near horizons, these fluctuations can have observable effects. The Hawking radiation from black holes arises from quantum fluctuations near the event horizon. Similar processes might occur at cosmic event horizons, producing a faint thermal glow. These quantum effects are extraordinarily weak for cosmic horizons, far too weak to detect with any conceivable technology, but they are predicted by our best theories. If quantum gravity modifies these predictions, as some theories suggest it might, observing or constraining these effects could provide clues about physics beyond general relativity and quantum field theory, physics that operates at the intersection of gravity and quantum mechanics. The cosmic horizon as an information bottleneck represents a constraint on how much information can pass between different regions of the universe. Information has a maximum speed, the speed of light, and horizons represent barriers beyond which information cannot travel. In this sense, horizons act as bottlenecks, limiting the flow of information through the universe. The area of a horizon determines how much information can be encoded on it, according to the holographic principle. This relationship between area and information suggests that information is a fundamental concept in physics, perhaps more fundamental than matter or energy. Understanding how information behaves near horizons, how it is preserved or lost, how it flows and is encoded, might be the key to unifying quantum mechanics and general relativity and understanding the deepest nature of physical reality. What happens at the edge, according to physics, is therefore a complex tapestry of effects involving light, matter, information, and the structure of space-time itself. Nothing catastrophic occurs at the horizon itself. Yet from our distant vantage point, objects approaching the edge undergo a transformation, fading from view through infinite redshift, appearing to freeze in time, carrying information beyond our reach into a realm we can never access. These effects are not artifacts of measurement or limitations of technology, but fundamental consequences of living in an expanding universe with finite light speed, predictions of our best physical theories that have been confirmed by observation. Understanding these phenomena pushes the boundaries of physics, requiring us to grapple with quantum mechanics, general relativity, thermodynamics, and information theory simultaneously, and pointing toward a deeper synthesis that might finally explain how gravity and quantum mechanics fit together into a single coherent framework that describes reality at all scales, from the smallest to the largest. As we consider these exotic effects at cosmic boundaries, we naturally wonder how they might connect to even more speculative ideas about the nature of reality, whether our universe is unique or one among many. and what the existence of boundaries tells us about the possibility of other universes beyond our own cosmic horizon. Does space end, or does it just keep expanding? This question contains a subtle confusion that reveals how difficult it is to think clearly about the cosmos. The expansion of space and the potential endedness of space are two separate issues, not alternatives. Space could be infinite and expanding. Space could be finite and expanding. Space could even, in principle, be finite and not expanding, though our universe is not like this. The expansion describes how space changes over time, how distances between objects grow, how the fabric of the cosmos stretches. The question of whether space ends asks about the spatial extent of the universe, whether there is a boundary beyond which nothing exists. These are independent questions, and disentangling them requires careful thinking about what we mean by space, by expansion, and by the universe itself. The answer that emerges from modern cosmology is strange and counterintuitive, suggesting that space most likely has no end, extending infinitely in all directions, while simultaneously expanding everywhere, with every region of space growing larger, carrying galaxies apart, even though there is no edge from which the expansion proceeds and no center from which it emanates. The expansion of space is not an expansion into anything. This is perhaps the single most important and most difficult concept to grasp about cosmic expansion. When we think of things expanding in everyday life, they expand into surrounding space. A balloon expands into the air around it. A city expands into the countryside surrounding it. But the universe does not expand into some pre-existing void or surrounding space. Space itself is expanding, and there is nothing outside of space for it to expand into. The very concept of outside requires space, requires dimension and distance, and if we are talking about all of space, there is no outside. This is not a limitation of measurement or observation, but a fundamental conceptual point. The universe is not a thing in space, it is space itself, along with all the matter and energy it contains. When cosmologists say space is expanding, they mean that the distance between any two points that are not bound together by gravity is increasing over time. A meter stick placed between two galaxies would not stretch, but new space would appear. Or more accurately, the space that exists would grow, increasing the number of meter sticks that would fit between the galaxies. The infinite extent of space is compatible with expansion in ways that finite extent would not necessarily be. If space is infinite, then it has always been infinite, even at the moment of the Big Bang. This sounds paradoxical, because we tend to think of the Big Bang as a point, a singularity from which everything exploded. But the Big Bang was not an explosion in space. It was an explosion of space. If space is infinite now, it was infinite then, just infinitely dense rather than infinitely extended in the way we think of extension. An infinite universe can start in an infinitely dense state, where every point is compressed to infinite density, then expand so that the density decreases over time, while the infinity remains. Imagine an infinite grid of points, all compressed together. Then imagine pulling that grid apart uniformly so that the spacing between points increases. The grid was always infinite, but the distance between points changes. This is what expansion means in an infinite universe. The closed, flat, and open geometries of space determine whether the universe is finite or infinite, but do not determine whether it expands. These geometries come from general relativity, which describes how mass and energy curve space-time. A closed universe has positive curvature, like the surface of a sphere. If you travel in any direction in a closed universe, you eventually return to your starting point, like traveling around a sphere. A closed universe is finite in extent, but has no boundary, no edge. The surface of a sphere has finite area but no edge. A flat universe has zero curvature, following Euclidean geometry. Parallel lines never meet. Triangles have angles summing to 180 degrees. A flat universe can be infinite, extending forever in all directions. An open universe has negative curvature, like a saddle. An open universe is always infinite. Current observations indicate our universe is very close to flat, so close that we cannot measure any curvature, which suggests it is either exactly flat or so large that the curvature is negligible over observable scales. A flat universe is most naturally infinite, and this is what most cosmologists believe our universe to be. The topology of space is separate from its geometry and introduces additional possibilities for whether space ends. Topology describes how space is connected, whether it wraps around on itself or extends forever. A flat geometry can have different topologies. The simplest is Euclidean space, infinite and simply connected, extending forever in all directions without wrapping around. But flat space could also have a toroidal topology, like a three-dimensional version of a video game screen, where leaving one edge brings you back at the opposite edge. In such a universe, space would be flat locally, but finite globally. You could travel in a straight line and eventually return to where you started without ever encountering an edge. Current observations place limits on the minimum size such a topology could have. If the universe wraps around, it does so on scales much larger than the observable universe, so large that we see no repeating patterns that would indicate wraparound. This means that even if space is finite topologically, it is so vast that it might as well be infinite for all practical purposes. The conformal structure of space-time describes how light propagates, and therefore how information spreads through the cosmos. In an expanding universe, the conformal structure determines which events can influence which other events, which regions can communicate, which observations are possible. This structure is independent of whether space is finite or infinite. An infinite universe with accelerating expansion has a finite conformal structure, in the sense that there is a maximum distance from which light can ever reach any given observer. A finite universe could, depending on its topology and expansion rate, have a conformal structure that allows light to circle the universe multiple times, creating strange observational effects like seeing multiple images of the same galaxy in different directions. The relationship between expansion and conformal structure explains why we have cosmic horizons, why there are limits to what we can observe, even if space itself extends infinitely beyond those limits. The cosmic expansion rate is described by the Hubble parameter, which relates the velocity at which objects recede from us to their distance. The Hubble parameter is not constant in time, but changes as the universe evolves, depending on the relative amounts of matter, radiation, and dark energy. In the early universe, dominated by radiation and matter, the expansion was slowing down due to gravity. In the current era, dominated by dark energy, the expansion is accelerating. The Hubble parameter determines how quickly space expands, how rapidly distances grow, but it does not tell us whether space is finite or infinite. An infinite space can expand slowly or quickly, and a finite space can do the same. What the Hubble parameter does tell us is that at any given moment, objects at a certain distance are receding from us at the speed of light due to the expansion of the intervening space. This distance, called the Hubble radius, is about 14 billion light-years currently. Objects farther than the Hubble radius are receding faster than light, not because they move through space faster than light, but because the space between us and them is expanding so rapidly. The difference between recession velocity and peculiar velocity is crucial for understanding expansion. Recession velocity is the apparent velocity due to the expansion of space, calculated by multiplying distance by the Hubble parameter. Peculiar velocity is the actual motion of an object through space relative to the expansion. Galaxies have peculiar velocities of a few hundred to a few thousand kilometers per second due to gravitational interactions with nearby galaxies. These peculiar velocities are tiny compared to recession velocities for distant galaxies. A galaxy 10 billion light-years away has a recession velocity many times the speed of light due to cosmic expansion, while its peculiar velocity through space remains ordinary. The recession velocity is not limited by the speed of light because it is not motion through space, but the expansion of space itself. Objects can recede from us faster than light without violating relativity because the special relativistic speed limit applies to motion through space, not to the rate at which space itself can expand. The scale factor is the quantity cosmologists use to describe how much the universe has expanded. If the scale factor doubles, all distances in the universe double, all wavelengths of light stretch by a factor of 2, all temperatures drop by half. The scale factor was nearly 0 at the Big Bang and has been increasing ever since. Currently, it increases by about 7% every billion years. The scale factor will continue increasing forever if dark energy remains constant or grows, meaning the expansion will never stop or reverse. Whether space is finite or infinite, the scale factor describes how it changes. An infinite space with a scale factor that increases by 50% becomes a larger infinity in a sense, with distances between objects 50% greater, even though the total extent remains infinite. This might seem paradoxical, but mathematically it is perfectly consistent. Infinity plus infinity is still infinity, but the distribution of matter within that infinity changes as expansion proceeds. The concept of comoving coordinates helps clarify what expansion means. Comoving coordinates are a coordinate system that expands with the universe, such that objects at rest with respect to the cosmic expansion maintain fixed comoving coordinates, even as the physical distances between them grow. Imagine a grid painted on expanding space, with galaxies sitting at grid intersections. As space expands, the grid expands with it, and the galaxies remain at the same grid coordinates, even though the physical distance between grid lines increases. In comoving coordinates, the universe appears static, with galaxies maintaining fixed positions. Only when we measure physical distances do we see the expansion. This coordinate system is useful because it separates the expansion of space from the motion of objects through space. A galaxy at rest in comoving coordinates is simply being carried along by expansion, while a galaxy moving through comoving coordinates has peculiar velocity. The proper distance between objects changes with time due to expansion, while comoving distance remains constant for objects at rest with respect to the expansion. Proper distance is what you would measure if you could freeze the universe, stop expansion, and lay rulers end to end between 2 points. This is the distance that appears in everyday notions of how far away something is. Proper distance to distant galaxies increases continuously as the universe expands. A galaxy that is 10 billion light-years away in proper distance today will be farther away tomorrow, simply because space has expanded in the interim. Co-moving distance, by contrast, factors out the expansion. A galaxy at fixed co-moving distance remains at that co-moving distance even as proper distance increases. The relationship between proper and co-moving distance is given by the scale factor. Proper distance equals co-moving distance times the scale factor. As the scale factor grows, proper distances grow proportionally, while co-moving distances remain fixed. The misconception that expansion creates new space from nothing is understandable, but not quite accurate. Expansion does not create space in the sense of conjuring something from nothing. Rather, space that already exists grows or stretches. The distinction is subtle, perhaps even semantic, but it matters philosophically. If space is infinite, expansion does not make it more infinite or add to its extent. If space is finite, expansion increases its volume. But this is not the creation of space so much as the growth of space that already existed in a smaller state. The energy contained in space, including the energy of fields, like the dark energy field, does increase as space expands, because dark energy has constant density, and more volume means more total energy. This apparent violation of energy conservation is allowed in general relativity, because energy conservation, as we normally understand it, applies in flat spacetime with a time-independent metric, conditions that do not hold in an expanding universe. The balloon analogy for cosmic expansion is useful but limited and often misinterpreted. In this analogy, the surface of an expanding balloon represents space, and dots drawn on the surface represent galaxies. As the balloon inflates, the dots move apart, not because they move through the surface, but because the surface itself expands. This illustrates how galaxies recede from each other without moving through space. The analogy captures important features. There is no center to the expansion on the surface. Every dot sees every other dot receding, and the expansion is uniform. However, the analogy has limitations. The balloon surface is two-dimensional, embedded in three-dimensional space, and the expansion occurs into that three-dimensional space. This suggests cosmic expansion occurs into some higher dimensional space, but this is not the case. Our three-dimensional space is not embedded in a higher dimensional space in any sense we need for understanding expansion. The expansion of the universe does not require or imply extra dimensions. The embedding of space in higher dimensions is a mathematical technique, not a physical necessity. Mathematicians can prove that any curved space can be embedded in a flat space of sufficiently high dimension, meaning you can represent the curved space as a surface within a higher dimensional space. This is useful for visualization and calculation, but does not mean the higher dimensional space physically exists. Our universe could be a three-dimensional space with curvature, existing entirely on its own, without being embedded in anything. The expansion happens within this space, according to rules determined by general relativity and the distribution of matter and energy. No external space is needed for expansion to occur. The notion of expanding into something is a holdover from thinking about objects expanding in space rather than space itself expanding. The cosmological constant represents a possible form of dark energy that would cause eternal exponential expansion. If the cosmological constant is positive, as observations suggest, space will expand forever, with the expansion rate approaching a constant positive value. In this scenario, the scale factor grows exponentially, doubling at regular intervals. Distances grow without bound, and the universe becomes increasingly empty and cold as matter and energy are diluted by the growing volume. The cosmological constant is equivalent to a vacuum energy, an energy inherent in empty space itself, with the strange property that its density remains constant even as space expands. This means more dark energy appears as space grows, driving continued acceleration. Whether space is finite or infinite, exponential expansion driven by a cosmological constant means distances grow forever, with no end to the expansion in time. If space is infinite, it remains infinite while expanding. If space is finite, its volume grows exponentially, approaching infinite volume asymptotically, though never quite reaching it in finite time, if the expansion is exponential. The question of whether space is created at expansion asks whether new space comes into being or existing space stretches. This question may not have a definitive answer, because creation and stretching might not be meaningfully distinct at a fundamental level. In general relativity, space and time together form space-time, a four-dimensional manifold. The expansion of space is a change in the metric, the mathematical object that describes distances and time intervals. Whether we describe this change as creating new space or stretching existing space is a matter of interpretation, not a difference in the physical content of the theory. What general relativity tells us unambiguously is that the proper distance between distant objects increases, that the metric evolves according to Einstein's equations, and that the universe had a state of higher density in the past and will have a state of lower density in the future. The language of creation versus stretching is our attempt to translate this mathematics into intuitive terms, but the intuition may simply not apply at cosmic scales. The Friedmann equations govern the expansion of the universe, relating the expansion rate to the energy content of space. These equations are solutions to Einstein's field equations, applied to a homogeneous and isotropic universe. The Friedmann equations tell us that the expansion rate depends on the sum of the energy densities of all forms of matter and energy: ordinary matter, dark matter, radiation, and dark energy. In the early universe, radiation dominated, and the expansion rate was high. As the universe expanded and cooled, radiation density decreased faster than matter density, and matter took over as the dominant component. Currently, dark energy dominates, and the expansion rate is increasing. The Friedmann equations apply regardless of whether space is finite or infinite. They describe how the scale factor evolves, how distances grow, but they do not specify the total extent of space. A universe satisfying the Friedmann equations could have any spatial topology compatible with homogeneity and isotropy. The initial conditions of the universe determine its fate to some extent. If the universe started with a certain density and expansion rate, the Friedmann equations determine how it evolves. However, without knowing the initial conditions precisely, we cannot say definitively whether space is finite or infinite. Inflation, the period of exponential expansion in the first fraction of a second after the Big Bang, complicates this because inflation can take a small region and expand it to enormous size, potentially much larger than the currently observable universe. If inflation occurred, the universe we observe is just a tiny fraction of the whole, a small patch that was inflated from a minuscule region. This patch could be part of an infinite space, or it could be part of a finite space so large that the curvature is undetectable. Inflation erases information about initial conditions by smoothing out irregularities and flattening curvature, making it difficult to determine whether the total universe is finite or infinite based on observations of our local patch. The holographic principle suggests that the information content of a region of space is proportional to its surface area rather than its volume. This principle, inspired by black hole thermodynamics, implies that a finite area can encode all the information about what lies within a volume, suggesting the volume might be emergent or derivative rather than fundamental. If the holographic principle is correct and applies to the entire universe, it has profound implications for whether space is fundamentally three-dimensional or whether three-dimensional space emerges from information encoded on a two-dimensional boundary. In an infinite universe, the holographic principle becomes difficult to formulate because there is no finite boundary to encode the infinite interior. Some versions of holography work only for finite regions or for specific geometries. The application of holography to cosmology remains speculative. But if it proves correct, it might tell us that the question of whether space is infinite or finite is less fundamental than it appears. That what really matters is the information structure rather than the spatial extent. The steady-state theory, now discredited, proposed that the universe expands but remains essentially unchanged because new matter is continuously created to fill the gaps left by expansion. In this model, space expands forever, densities remain constant, and the universe has no beginning or end in time. The steady-state theory required the spontaneous creation of matter, about 1 hydrogen atom per cubic meter per billion years, to compensate for the dilution caused by expansion. This theory predicted no cosmic microwave background radiation, no evolution of galaxies over time, and no Big Bang. Observations, particularly the discovery of the cosmic microwave background and the evolution of quasars and galaxies, ruled out the steady-state model. The universe did have a dense, hot beginning and does evolve over time. However, the steady-state theory illustrates that expansion and creation are logically independent. A universe can expand with or without creating matter, and in our universe, as best we understand it, expansion occurs but matter is not created, only diluted. The multiverse hypothesis suggests that our universe is one of many, possibly infinitely many, separate universes. In some multiverse models, these other universes are separate regions of an infinite space, regions that inflated from different initial conditions, or where the laws of physics take different forms. In other models, the universes are truly separate, disconnected spacetimes with no physical relation to each other. If the multiverse exists and consists of separate spatial regions in an infinite space, then space certainly does not end at the boundary of our observable universe, but continues through countless other bubble universes. Each universe or bubble expands according to its own dynamics, potentially with different values of physical constants or different amounts of dark energy. The expansion of one bubble is independent of others, and the space between bubbles may itself be expanding, driven by ongoing inflation in the regions that have not yet formed bubble universes. The ultimate fate of an expanding universe depends on the nature of dark energy. If dark energy is a cosmological constant, the expansion will continue accelerating forever, approaching exponential expansion. The universe will become increasingly cold, dark, and empty, with galaxies outside our local cluster disappearing beyond the cosmic event horizon. Stars will burn out, black holes will evaporate, and eventually, even protons may decay. In the extreme far future, the universe will consist of a thin soup of photons, neutrinos, and perhaps other stable particles in an ever-expanding space. If dark energy weakens over time, the expansion might decelerate, though current evidence suggests it will not reverse entirely. If dark energy increases over time, the expansion could accelerate without bound, tearing apart galaxies, stars, planets, and eventually atoms in a big rip. The fate of expansion determines the fate of all structure in the universe, but it does not tell us whether space is fundamentally finite or infinite, only how the space we observe will evolve. The anthropic principle provides one answer to why we observe the universe to be so large and old, because a smaller, younger universe could not have produced observers to wonder about it. Stars need time to form, to synthesize heavy elements, and to die so that those elements can be incorporated into planets. Life needs billions of years to evolve. The age and size of the observable universe are related through the speed of light. An older universe necessarily has a larger observable region because light has had more time to travel. We observe a universe billions of years old and tens of billions of light years in extent because that is the minimum size and age needed for observers like us to exist. This does not tell us whether the total universe is infinite, but it explains why our observable patch is as large as it is. The difference between space expanding and galaxies moving through space is not always clear-cut, especially over short distances. Galaxies in our local group, such as Andromeda, are actually approaching the Milky Way due to gravitational attraction. Their peculiar velocities, their motion through space, overcome the recession velocity from expansion. Only for galaxies far enough away that their recession velocity exceeds their peculiar velocity does expansion dominate. This transition occurs at a distance of a few tens of millions of light years. Beyond this scale, galaxies generally recede due to expansion, though gravitational interactions within clusters can still produce peculiar velocities. The expansion of space is therefore a large-scale phenomenon, noticeable only when averaged over vast distances. On smaller scales, gravity, electromagnetism, and other forces determine the behavior of matter, and expansion is negligible. The meaning of infinite in the context of an infinite universe requires clarification. Mathematically, infinity is not a number, but a concept describing something without bound. An infinite universe is one where you can travel in any direction forever and never reach an edge. This does not mean you can reach infinitely distant places, because travel takes time and light speed limits how far you can go in finite time. An infinite universe is compatible with horizons and unreachable regions. In fact, in an infinite expanding universe with accelerating expansion, almost all of the universe is beyond our event horizon, forever unreachable and unobservable. The infinity of space does not imply that everything is accessible or knowable, only that there is no boundary beyond which space ceases. The finite speed of light creates a fundamental limit on what we can know about whether space is finite or infinite. Even if space is infinite, we can observe only a finite region, the region from which light has had time to reach us. If space is finite, but much larger than the observable universe, we cannot tell the difference observationally. Distinguishing between a very large finite universe and an infinite universe requires either observing repeating patterns, if the universe has a periodic topology, or measuring the curvature of space, if the universe is closed. Current observations show no repeating patterns and measure the curvature to be consistent with zero, suggesting the universe is either flat and infinite, or so large that we cannot detect its curvature or periodicity. Future observations with more sensitive instruments might detect slight curvature or find repeating patterns. But for now, we cannot say definitively whether space is finite or infinite. The expansion of space can be thought of as a global stretching where local regions are carried apart without experiencing forces. Objects that are sufficiently far from each other experience no direct force pushing them apart. Yet the distance between them increases because the space containing them expands. This is possible because in general relativity, the motion of objects is determined not by forces in the Newtonian sense, but by the curvature of spacetime. Freely falling objects follow geodesics, the straightest possible paths through curved spacetime. In an expanding universe, geodesics diverge, meaning objects at rest with respect to the expansion naturally move apart. This divergence is not due to a force, but to the geometry of spacetime itself. The expansion is encoded in the metric, and objects simply follow the natural geometry. The conservation of energy in an expanding universe is subtle and often misunderstood. In a static spacetime with time translation symmetry, energy is conserved. But in an expanding universe, spacetime is not static, and time translation symmetry is broken. General relativity does not guarantee energy conservation in such circumstances. Photons, for example, lose energy as the universe expands due to redshift. Where does this energy go? It is not transferred to anything else. It simply disappears. Similarly, dark energy density remains constant as space expands, meaning the total dark energy increases. This energy is not coming from anywhere. It is simply appearing as space grows. In general relativity, energy conservation applies locally, but not necessarily globally in an expanding universe. This does not violate any fundamental principle, because energy conservation is a consequence of symmetries, and when those symmetries are absent, conservation laws need not hold. The empty space or vacuum has properties that affect cosmic expansion. Quantum field theory tells us that even empty space, devoid of particles, contains quantum fields in their ground state. These fields have energy, called vacuum energy or zero-point energy, arising from quantum fluctuations. The vacuum energy contributes to the stress-energy tensor in Einstein's equations, affecting the curvature of space-time and the expansion rate. If the vacuum energy is positive, it acts like a cosmological constant, causing accelerating expansion. If the vacuum energy is zero or negative, different dynamics result. The measured value of vacuum energy, inferred from the accelerating expansion, is tiny but positive, suggesting that empty space has a small inherent energy that drives acceleration. Whether space is finite or infinite, this vacuum energy exists throughout, affecting expansion everywhere. The size of the universe, if finite, is difficult to estimate. If the universe is closed, having positive curvature like a three-dimensional sphere, its size is related to the radius of curvature. Current observations constrain the radius of curvature to be at least hundreds of billions of light years, possibly much larger. If the universe is flat, but has a non-trivial topology that makes it finite, its size depends on the specific topology. A toroidal universe, for example, could be relatively small if the torus has small circumference in some directions. Observations looking for repeating patterns or topological effects constrain the minimum size of such a universe to be larger than the observable universe, but exact limits depend on the topology assumed. The safest conclusion from current data is that if the universe is finite, it is at least several times larger than the observable universe, and possibly vastly larger, or even infinite. The rate of expansion can exceed the speed of light, as measured by how fast distances grow. A galaxy 10 billion light-years away is receding at over twice the speed of light due to expansion. This is allowed because the speed of light limit applies to motion through space, not to the rate at which space expands. The expansion rate is proportional to distance, so sufficiently distant objects always recede faster than light. This is encoded in the Hubble law, which states recession velocity equals the Hubble constant times distance. Since the Hubble constant is positive, there is always a distance, the Hubble radius, at which recession velocity equals light speed, and beyond which recession exceeds light speed. This faster-than-light recession does not allow superluminal travel or communication because you cannot catch up to a receding galaxy by moving through space. The expansion of space carries it away faster than you can approach. The ultimate question of whether space ends cannot be answered with certainty based on current observations. Physics provides tools to explore the question and constraints on possible answers, but the data do not definitively resolve whether space is finite or infinite. The expansion of space is well established, observed through the redshift of distant galaxies and the cooling of the cosmic microwave background. But expansion is compatible with either a finite or infinite universe. Most cosmologists favor an infinite universe because observations show space is very close to flat, and flat space is naturally infinite unless it has exotic topology. An infinite universe is also simpler in some ways, avoiding questions about what lies beyond the boundary of a finite universe. However, simplicity is not proof, and the possibility of a finite universe remains open. The answer may forever remain uncertain if the universe is much larger than we can observe, for in that case, we lack the data to distinguish between a very large finite universe and an infinite one. As we contemplate whether space ends or expands forever, we find ourselves drawn to consider what the expansion itself means for the nature of existence, whether the growth of space implies a beginning or allows for eternal duration, and how the expansion connects to the fundamental question of why there is something rather than nothing. A question that leads us beyond physics into the deepest mysteries of being itself. What the edge of the universe looked like in the past is a question that inverts our usual thinking about cosmic observation. When we observe distant objects, we are looking backward in time, seeing ancient galaxies as they were billions of years ago. But when we ask what the edge looked like in the past, we are asking something different. We are asking what an observer in the early universe would have seen if they looked toward the horizon of their observable universe, what the cosmic boundary looked like when the universe was young, hot, and dense. The answer reveals a cosmos radically different from what we see today, a universe where the edge was not dark and distant, but bright and close, where the horizon glowed with the light of creation itself, where the boundary was not a fade into invisibility, but a wall of blazing plasma. Understanding how the edge has evolved from this brilliant beginning to the cold darkness we observe today traces the entire thermal history of the cosmos, showing how structure emerged from uniformity, how darkness replaced light, and how the universe transformed from a compact furnace to the vast, cold expanse we inhabit. The surface of last scattering represents the edge as it appeared roughly 380,000 years after the Big Bang. This surface is not a physical boundary, but a moment in time when the universe became transparent, when electrons and protons combined to form neutral hydrogen atoms and photons could suddenly travel freely. Before this recombination, the universe was opaque, filled with a hot plasma where photons were constantly scattered by free electrons. An observer in this epoch would see no distant galaxies, no stars, nothing beyond a short distance, because light could not propagate freely. The observable universe of such an observer would be tiny, perhaps a few light years across, bounded not by the limit of how far light had traveled, but by the opacity of the surrounding plasma. The edge would appear as a glowing fog in all directions, similar to being inside a luminous cloud. This fog would be intensely bright because the plasma was hot, at a temperature of about 3,000 degrees Kelvin, hot enough to glow with visible light. The entire sky would shine with the orange-red glow of this plasma, with no darkness anywhere, no stars, no structure, just uniform radiance. The moment of recombination marked a dramatic transformation of the cosmic edge. As the universe expanded and cooled, reaching the critical temperature where electrons could bind to protons without being immediately ionized by ambient radiation, the opacity suddenly dropped. Within a relatively short time, perhaps a few tens of thousands of years, the universe went from completely opaque to nearly transparent. An observer present during this transition would have witnessed the edge changing from a glowing wall to a receding surface. As recombination proceeded, the glowing plasma that defined the edge moved farther away, because light could now travel from more distant regions. The observable universe would have grown rapidly, revealing vast expanses of space previously hidden by opacity. However, there would still be nothing to see in these newly revealed regions because no stars had yet formed. The universe after recombination was dark, filled only with neutral hydrogen gas, beginning what cosmologists call the cosmic dark ages. The cosmic dark ages lasted for perhaps 100 million to several hundred million years, an era when the universe was transparent but contained no sources of light. During this period, the edge of the observable universe, as viewed by a hypothetical observer, would have appeared as absolute darkness in most directions. The only light would come from the cooling radiation left over from recombination, which would be redshifted and fading as the universe expanded. This radiation would no longer appear as visible light, but would shift through infrared to microwave wavelengths. An observer in the Dark Ages would inhabit a universe where the horizon was black, where nothing shone except the fading afterglow of creation, growing redder and dimmer with each passing moment. This darkness was not the darkness of empty space as we imagine it today, where a few distant galaxies provide faint points of light. It was absolute darkness, with no stars, no galaxies, no structure, nothing but neutral hydrogen gas slowly collapsing under its own gravity in regions where density was slightly higher than average. The formation of the first stars transformed the edge from darkness to the dawn. When the first stars ignited, perhaps 200 million years after the Big Bang, they were likely very massive, hundreds of times the mass of the Sun, burning intensely hot and bright. These population 3 stars, as they are called, contained only hydrogen and helium because no heavy elements had yet been created. They burned through their fuel quickly, living only a few million years before exploding as supernovae. The light from these first stars would have been visible to great distances because there was no dust to obscure them, no intervening galaxies to block the view. An observer a few hundred million years after the Big Bang, positioned in a region where stars had not yet formed, would look toward the horizon and see scattered points of brilliant blue-white light, the first stars, marking regions where star formation had begun. These lights would be few and isolated at first, but as more stars formed and the first galaxies assembled, the edge would become increasingly populated with luminous objects. The epoch of reionization fundamentally altered the appearance of the cosmic edge once again. Reionization began when the ultraviolet light from the first stars and galaxies became intense enough to ionize the neutral hydrogen gas filling the universe. This process was gradual and patchy, occurring earlier in some regions than others, depending on where star formation was most vigorous. As reionization proceeded, bubbles of ionized gas expanded around galaxies and merged, eventually filling all of space. An observer during reionization would see a heterogeneous edge, with some regions glowing with the ultraviolet light from young galaxies, while other regions remained dark, still filled with neutral hydrogen. The boundary between ionized and neutral regions would be sharp, creating a complex bubble-like structure on the largest scales. This epoch lasted from perhaps 200 million to 1 billion years after the Big Bang, and during this time, the appearance of the edge would have been constantly changing as ionized regions grew and merged. The transparency of the reionized universe allowed light to travel freely across cosmic distances, but the edge still looked vastly different from today. Early galaxies were smaller, less organized, and more actively forming stars than galaxies today. They were also more numerous within a given volume, because the universe was denser and galaxies had not yet merged into the large structures we see now. An observer 1 billion years after the Big Bang, looking toward the edge of their observable universe, would see a sky densely packed with small, irregular, intensely star-forming galaxies. These galaxies would appear very blue because they were forming massive stars at prodigious rates, and massive stars are blue. The sky would be much brighter than it appears to us because galaxies were closer together and more luminous. However, the most distant visible objects would still be significantly redshifted, appearing redder than their intrinsic color due to the expansion of space during the light's journey. The quasar epoch represents another distinctive appearance of the cosmic edge, occurring roughly 1 to 3 billion years after the Big Bang. Quasars are supermassive black holes at the centers of galaxies, accreting matter at enormous rates and shining with the luminosity of trillions of suns. During the quasar epoch, these objects were far more common than they are today. An observer during this era, looking toward the horizon, would see quasars as brilliant points of light, outshining entire galaxies scattered across the sky. The edge would be populated by these beacons, marking the locations of massive black holes and the galaxies hosting them. The light from quasars was so intense that it could affect surrounding gas across vast distances, ionizing it and heating it, creating large-scale bubbles of hot gas around each quasar. The appearance of the edge during the quasar epoch would have been dramatic, with intensely bright points surrounded by glowing halos of ionized gas. The evolution of galaxy morphology changed how the edge appeared as the universe aged. Early galaxies were predominantly irregular and clumpy, lacking the organized spiral and elliptical structures common today. They were undergoing violent star formation, with gas collapsing rapidly into dense regions and forming massive star clusters. As time passed and galaxies merged and evolved, they became larger, more organized, and less actively star-forming. An observer at the edge of the observable universe, several billion years after the Big Bang, would see a transition in galaxy appearance, with older, more organized galaxies in nearer regions, and younger, more chaotic galaxies in more distant regions. This gradient reflects cosmic evolution, the tendency for structure to develop over time, as gravity amplifies small density variations into the complex patterns we observe today. The cosmic web emerged gradually over billions of years, transforming the appearance of large-scale structure near the edge. In the very early universe, matter was distributed almost uniformly, with only tiny density variations of about 1 part in 100,000. Over time, gravity amplified these variations, pulling matter together into filaments, sheets, and clusters, separated by vast voids. An observer in the early universe would not have seen this web structure, because it had not yet formed. The edge would have appeared relatively uniform, with galaxies distributed more or less evenly. As billions of years passed and structure developed, the edge would take on the filamentary appearance we see today, with dense regions connected by tendrils of galaxies and separated by large empty spaces. This evolution of structure is one of the most important changes in how the edge has appeared over cosmic history. The density of the universe has decreased by a factor of millions since the early epochs, changing the appearance of the edge profoundly. In the first billion years, galaxies were packed much more closely together. The average distance between galaxies was perhaps 10 times smaller than today, meaning galaxies were 1,000 times more concentrated in volume. An observer in this denser universe would see many more galaxies within their observable volume, and those galaxies would be closer together, creating a sky far more crowded with visible objects than what we observe. As the universe expanded, this density decreased, and galaxies moved farther apart. The edge today appears sparse compared to the dense cosmic environment of the early universe, with vast distances separating galaxy clusters and enormous voids containing very little visible matter. The metallicity of gas and stars has increased over cosmic time, subtly affecting how the edge appears. Metallicity refers to the abundance of elements heavier than hydrogen and helium, which astronomers collectively call metals, even though they include elements like carbon, oxygen, and nitrogen that are not metals in the chemical sense. The first stars contained essentially no metals because they formed from the pristine gas created in the Big Bang. When these stars died, they ejected metals into space, enriching the gas from which subsequent generations of stars formed. An observer in the early universe, looking at the edge, would see stars and galaxies composed almost entirely of hydrogen and helium. These population 3 stars would have been very massive and very blue. As time passed and metals accumulated, stars became smaller and redder on average, and galaxies began to contain dust, which absorbed and scattered light. The edge today appears redder and dustier than it did in the past, because galaxies have accumulated metals and dust over billions of years of stellar evolution. The merger history of galaxies created a different distribution of galaxy sizes and types near the edge at different epochs. In the early universe, most galaxies were small, with masses of billions rather than hundreds of billions of solar masses. These small galaxies frequently collided and merged, gradually building up the large galaxies we see today. An observer in the early universe would see many small galaxies near the edge, with large galaxies being rare. Today, an observer sees a mix of large and small galaxies, with giant ellipticals and massive spirals common in galaxy clusters. The edge has evolved from being populated primarily by dwarf galaxies to being populated by galaxies of all sizes, reflecting the hierarchical growth of structure where small objects merge to form larger ones. The rate of star formation across the universe has declined significantly from its peak about 10 billion years ago. During the peak epoch, galaxies were forming stars at rates 10 to 100 times higher than typical star formation rates today. An observer during this era, looking toward the edge, would see galaxies blazing with the light of newly formed stars. The edge would appear brighter and bluer because star formation produces primarily young, hot, blue stars, and these were far more abundant then than now. As the universe aged and gas was consumed by star formation, or heated by various processes, the star formation rate declined. The edge today appears redder and dimmer because galaxies have exhausted much of their gas supply and are forming stars at reduced rates. This decline in star formation is one of the most dramatic changes in cosmic history, representing a shift from a young, vibrant universe to an aging one approaching its long, slow decline toward darkness. The temperature of the cosmic microwave background radiation has decreased by a factor of more than 1,000 since recombination, changing its appearance dramatically. At recombination, this radiation had a temperature of about 3,000 Kelvin and appeared as visible orange-red light. An observer just after recombination would see this radiation as a luminous glow filling the entire sky. As the universe expanded, the wavelength of this radiation was stretched by the expansion, shifting it through infrared to microwave wavelengths. Today, the cosmic microwave background has a temperature of about 3 Kelvin, just a few degrees above absolute zero, and appears as microwave radiation invisible to human eyes. An observer today looking toward the edge sees this radiation not as light, but as a faint microwave signal, detectable only with specialized instruments. The edge has gone from glowing visibly to radiating at wavelengths far outside the visible spectrum, marking the cooling of the universe over cosmic time. The angular size of objects near the edge changes in counterintuitive ways due to the expansion of space and the finite speed of light. An object at a given comoving distance would have appeared larger in angular size in the past than it does today, even though it was farther away in proper distance. This occurs because light from the object was emitted when the universe was smaller, and the object subtended a larger angle on the sky of an observer at that time. As the universe expanded, the angular size of distant objects decreased. An observer in the early universe would see objects near their edge, appearing larger than we see similar objects at our edge today, even accounting for differences in intrinsic size. This is one of many counterintuitive effects arising from the interplay of expansion and light travel time. The horizon distance has grown continuously since the Big Bang, meaning the edge has moved steadily outward in comoving coordinates. In the first moments after the Big Bang, the horizon was tiny, encompassing a region smaller than an atom today. As time passed and light traveled farther, the horizon expanded, incorporating more and more of the universe into the observable region. An observer at any time in cosmic history would see a horizon at a certain distance, but that distance would be growing. The rate of growth depends on the expansion history of the universe. In the radiation-dominated era, the horizon grew rapidly relative to the size of the universe. In the matter-dominated era, it continued to grow but more slowly. In the current dark energy-dominated era, the horizon grows more slowly still, and eventually it will approach a limiting size beyond which it does not expand further in comoving coordinates. The edge has been receding throughout cosmic history, revealing more of the universe. But this recession will eventually stop as dark energy takes complete control. The velocity of recession for objects at the edge has varied over cosmic history in complex ways. In the early universe, when radiation and matter dominated, the expansion was decelerating, and objects at the edge were receding at lower velocities than they would have been if the expansion rate had been constant. During the matter-dominated era, the deceleration continued, but was less pronounced. In the current dark energy-dominated era, the expansion is accelerating, and objects at the edge are receding faster than they would have been in a decelerating universe. An observer measuring the recession velocity of objects at their horizon would find different values at different cosmic epochs, not because the edge is at a different physical location, but because the dynamics of expansion have changed. Objects that crossed the Hubble sphere, the distance at which recession velocity equals light speed, in the past might have later dropped back inside the Hubble sphere if the expansion decelerated enough, only to cross back out again as acceleration began. This complex motion reflects the changing dominance of different energy components. The entropy of the universe has increased dramatically since the Big Bang, and this is reflected in the appearance of the edge. Entropy measures disorder, and the second law of thermodynamics states that entropy always increases in closed systems. The early universe, despite being hot and dense, had very low entropy because it was highly uniform and in thermal equilibrium. As the universe expanded and cooled, structure formed, stars ignited, black holes appeared, and entropy increased. An observer in the early universe looking at the edge would see a simple, uniform distribution of matter and radiation. An observer today sees a complex, structured universe with galaxies, clusters, voids, and a wide range of temperatures and densities. This complexity represents higher entropy. The edge has evolved from simple uniformity to complex structure, and this evolution is a manifestation of the second law of thermodynamics operating on cosmic scales. The gravitational potential wells of the early universe were shallower and less numerous than today, affecting how the edge appeared. Gravitational potential wells are regions where gravity is strong, such as galaxy clusters. In the early universe, these wells were just beginning to form as small density perturbations grew under gravity. An observer then would see a relatively smooth distribution of matter, with only slight enhancements in certain regions. Today, gravitational potential wells are deep and well developed, with massive galaxy clusters containing thousands of galaxies. The edge has evolved from a nearly featureless gravitational landscape to one with deep wells and high peaks, representing the growth of structure under gravity over billions of years. The relative abundance of different types of radiation has changed over time, altering the spectrum of light coming from the edge. In the very early universe, the radiation was dominated by photons from the hot plasma, all at similar energies corresponding to the thermal equilibrium temperature. As stars formed, they added light at specific wavelengths determined by their temperatures and the emission lines of elements in their atmospheres. Quasars added intense continuum radiation across a broad spectrum. Supernovae added bright flashes of light at optical and ultraviolet wavelengths. Today, the spectrum of light from the edge is complex, containing contributions from stars, galaxies, quasars, the cosmic microwave background, and various other sources. An observer in the early universe would see a simpler spectrum dominated by thermal emission. An observer today sees a rich, multi-component spectrum, reflecting the diverse sources of light in the mature universe. The ionization state of intergalactic gas has varied over cosmic history, affecting the transparency of space, and therefore what can be seen at the edge. Before ionization, neutral hydrogen absorbed ultraviolet light efficiently, making the universe opaque to these wavelengths. After reionization, the hydrogen was ionized, and space became transparent to ultraviolet light. However, as the universe continued to expand and cool, some recombination occurred in dense regions, creating partially neutral gas that absorbed certain wavelengths. An observer at different epochs would find different degrees of transparency, with reionization marking a sharp transition from opaque to transparent. The edge in the neutral era would appear cut off at certain wavelengths because those photons could not propagate freely. The edge after reionization appears transparent across a broader range of wavelengths, allowing us to see farther in ultraviolet light. The magnetic fields in the universe have grown in strength and complexity since the early epochs, though their effects on the appearance of the edge are subtle. Magnetic fields in galaxies and clusters today are millions of times stronger than any primordial fields that might have existed in the early universe. These fields affect the polarization of light, the motion of charged particles, and the structure of gas in galaxies and clusters. An observer in the early universe looking at the edge would see minimal effects from magnetic fields because they were weak or absent. An observer today sees polarization patterns in the cosmic microwave background and in the light from galaxies that reflect the presence of large-scale magnetic fields. The edge has evolved from a magnetically quiet environment to one where magnetic fields play important roles in shaping structure and influencing the appearance of distant objects. The amount of dark matter relative to ordinary matter has not changed over cosmic time, but the distribution of dark matter has evolved significantly. Dark matter makes up about 85% of all matter, and this fraction has remained constant. However, dark matter was initially distributed almost uniformly, with only tiny density variations. Over time, gravity pulled dark matter together into halos, dense concentrations where galaxies would later form. An observer in the early universe looking at the edge would see the effects of dark matter only as slight gravitational enhancements in certain regions. An observer today sees the effects of dark matter as massive halos surrounding galaxies and clusters, lensing background light and holding structures together. the dark matter distribution near the edge has gone from nearly uniform to highly clumped, mirroring the evolution of visible structure. The role of dark energy has changed over cosmic history, transforming from negligible in the early universe to dominant today. In the radiation-dominated era, dark energy contributed a tiny fraction of the total energy density and had essentially no effect on the expansion. In the matter-dominated era, dark energy remained subdominant, but gradually grew in relative importance as matter density decreased with expansion. In the current era, dark energy dominates, controlling the expansion rate and causing acceleration. An observer in the early universe would have experienced a different cosmic expansion than we do, with deceleration rather than acceleration. The edge, as seen by that observer, would have been receding more slowly in some respects, and distant objects would have appeared slightly different than they do to us today. The transition from matter domination to dark energy. Domination is one of the most important changes in cosmic dynamics, and it has altered how the edge behaves and appears. The clustering of galaxies has increased dramatically since the early universe, changing the large-scale appearance of the edge. In the first billion years after the Big Bang, galaxies were distributed more uniformly, with only slight overdensities marking regions where clusters would eventually form. Over time, these overdensities grew, pulling in more galaxies and forming the clusters and superclusters we see today. An observer in the early universe looking at the edge would see a relatively smooth distribution of galaxies with no large clusters. An observer today sees the edge dominated by the cosmic web, with galaxies concentrated in filaments and clusters. This represents the growth of structure under gravity, a process that has been ongoing since the tiny density fluctuations of the early universe began to collapse. The types of active galactic nuclei have changed over cosmic history, with different classes dominating at different epochs. In the early universe, radio-loud quasars were common, powered by supermassive black holes, accreting gas at high rates. As the universe aged and gas supplies dwindled, these luminous quasars became rarer, replaced by less active galactic nuclei, and eventually by quiescent black holes, like the one at the center of our Milky Way. An observer in the early universe looking at the edge would see many bright quasars, making the edge a busy, luminous place. An observer today sees fewer quasars, with most supermassive black holes being dormant or only weakly active. The edge has gone from being populated by many energetic objects to being dominated by quieter, more evolved galaxies. The chemical composition of the universe has evolved from simple to complex, enriching the gas at the edge with heavy elements. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. All heavier elements were made inside stars and dispersed when stars died. In the early universe, gas at the edge was pristine, containing no metals. Today, even the most distant observable gas has been enriched to some extent by metals from earlier generations of stars. An observer in the early universe analyzing the spectrum of gas at the edge would see only hydrogen and helium lines. An observer today sees absorption and emission lines from many elements, including carbon, oxygen, silicon, and iron, indicating that the gas has been processed through stars. This chemical evolution is a one-way process, with metallicity increasing monotonically over time as more stars are born, live, and die. The duration of cosmic epochs has varied, with some lasting billions of years and others only millions. The radiation-dominated era lasted about 50,000 years. The matter-dominated era lasted about 9 billion years. The dark energy-dominated era began about 5 billion years ago and will continue forever if dark energy remains constant. An observer at different points in these epochs would have seen very different edges, not just in appearance, but in how rapidly the edge was changing. During the radiation-dominated era, conditions changed quickly, and the edge would have looked noticeably different over timescales of thousands of years. During the matter-dominated era, changes were slower, occurring over millions to billions of years. In the dark, energy-dominated era, changes are slower still, with the edge evolving on timescales of billions of years. The pace of cosmic evolution has been slowing down as the universe ages, meaning an observer in the future will see an edge that changes even more slowly than ours does today. The distance to the surface of last scattering has not changed in moving coordinates, but the proper distance to this surface has increased enormously since recombination. An observer at recombination would have been at the surface of last scattering themselves, surrounded by glowing plasma. As the universe expanded, this surface moved away in proper distance, even though it remained at the same moving coordinate. Today, the surface of last scattering is about 46 billion light-years away in proper distance, at the edge of the observable universe. This surface appears to recede from every observer at every time, creating a constantly expanding horizon. The light from this surface, the cosmic microwave background, has been redshifted by a factor of about 1,000 as space expanded during its journey to us. An observer in the future will see the same surface at even greater proper distance, redshifted even further, appearing cooler and fainter. The observable universe will continue to evolve in appearance, with the edge changing in predictable ways. As dark energy dominates more completely, the cosmic event horizon will stabilize, and galaxies currently visible will slip beyond this horizon and disappear from view. The edge will become darker and emptier as fewer galaxies remain observable. In the far future, trillions of years from now, only the local group of gravitationally bound galaxies will remain visible, with everything else having receded beyond the event horizon. An observer in this far future will see an edge vastly different from ours, much closer and much darker, containing only the merged remnants of the Milky Way and its neighbors. This represents the ultimate fate of the observable universe in a cosmos dominated by dark energy, a steady contraction of the observable region as acceleration pushes more and more galaxies beyond reach. What the edge of the universe looked like in the past reveals a cosmos in transformation, evolving from a hot, dense, uniform state to the complex, structured, cool universe we inhabit today. The edge has gone from glowing plasma to darkness, to scattered starlight, to the rich tapestry of galaxies we observe. It has receded from nearby to unimaginably distant, from bright to faint, from simple to complex. Each epoch of cosmic history left its mark on the appearance of the edge, and by observing distant objects, we see these ancient epochs preserved in light that has traveled for billions of years. The study of how the edge appeared in the past is therefore the study of cosmic evolution itself, a narrative written in the light from distant galaxies and the faint glow of the cosmic microwave background, telling the story of how the universe grew from simplicity to complexity, from uniformity to structure, from a blazing beginning to the vast, cold expanse we know today. Understanding how the edge has changed over cosmic time naturally leads us to wonder about the mechanisms that drove these changes, about the forces and phenomena that transformed the universe from its initial state, and about how the physical laws themselves have shaped the evolution of cosmic boundaries across billions of years of universal history. Could there be other universes beyond our edge? The answer depends entirely on what we mean by universe and what we mean by edge. If by universe we mean everything that exists, then by definition there can be nothing beyond it, no other universes, because the universe encompasses all of reality. But if by universe we mean our observable patch of space, the region from which light has had time to reach us, then almost certainly there is more beyond, perhaps infinitely more. And whether we call these distant regions part of our universe or separate universes becomes a matter of semantics rather than physics. The deepest version of this question asks whether there exist completely separate realms of space and time, causally disconnected from ours, with potentially different physical laws, different constants of nature, different dimensions, or different histories. This is the multiverse hypothesis, one of the most speculative and controversial ideas in modern cosmology and physics. The multiverse comes in many forms, from the relatively conservative idea that space extends beyond our horizon, to the radical proposal that quantum mechanics spawns infinite parallel realities with every measurement. And understanding these different versions requires carefully distinguishing between what is plausible, what is possible, what is testable, and what remains pure speculation. The quilted multiverse represents the most conservative and least controversial form of multiverse, emerging naturally from the assumption that space is infinite. If space extends infinitely in all directions beyond our observable universe, and if the laws of physics are the same everywhere, then somewhere in that infinite expanse, every possible arrangement of matter must occur. This follows from basic probability theory applied to infinite volumes. In a finite region of space, there are only finitely many ways to arrange atoms, even accounting for quantum uncertainty. If space is infinite, then every possible arrangement must occur somewhere, not just once, but infinitely many times. This means there must be regions of space, far beyond our horizon, that are identical to our observable universe, down to the last atom. There must be copies of you reading this sentence, copies of Earth, copies of the Milky Way, all scattered throughout infinite space at unimaginable distances. These are not separate universes in the sense of having different spacetimes or physical laws. They are simply distant regions of the same infinite space, beyond our ability to observe or interact with, but subject to the same physics that governs our local region. The distance to the nearest identical copy of our observable universe, assuming space is infinite and matter is distributed randomly, can be estimated mathematically. The calculation involves determining how many different possible configurations exist within a region the size of our observable universe, accounting for the number of particles and their quantum states. The result is a distance of roughly 10 to the power of 10 to the power of 118 meters, a number so large it defies comprehension. To put this in perspective, the observable universe is about 10 to the power of 26 meters across. The distance to an identical copy is incomprehensibly larger, requiring exponents stacked upon exponents to express. Yet in an infinite universe, such copies must exist, along with copies that are almost identical with only slight variations, copies where you made different decisions, copies where history unfolded differently, and copies of every conceivable variation within the laws of physics as we know them. The inflationary multiverse emerges from the theory of cosmic inflation, the rapid exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. Inflation solves several problems in standard Big Bang cosmology, explaining why the universe is so flat, so uniform, and why we see no magnetic monopoles or other exotic relics that should have been produced in the early universe. The inflationary multiverse arises from the recognition that inflation, once started, may never completely end everywhere. In most versions of inflation theory, the inflating region is unstable, and quantum fluctuations can cause inflation to end in some locations while continuing in others. When inflation ends in a region, that region reheats, creating matter and radiation, and becomes what we would recognize as a universe like ours. But inflation continues in surrounding regions, and in those regions, new pockets where inflation ends can form, creating additional universes. This process of bubble nucleation continues indefinitely, with inflation spawning new universes in a never-ending cascade. The eternal inflation scenario suggests that once inflation begins, it continues forever in a global sense, even though it ends locally in individual bubble universes. The space between bubbles is inflating exponentially, growing faster than the bubbles themselves expand, ensuring the bubbles never merge or collide in most cases. Each bubble universe has its own Big Bang moment when inflation ends locally, its own history, and potentially its own physical properties, if the physics that determines those properties is affected by the details of how inflation ends. An observer inside one bubble cannot see other bubbles because the intervening space is inflating so rapidly that light cannot cross the gap. Each bubble is causally isolated, a separate universe in the strongest sense, with no possibility of communication or interaction with other bubbles. The inflating space between bubbles acts as an impassable barrier, expanding faster than light can travel and ensuring permanent separation. The pocket universe description captures the structure of the inflationary multiverse. Each bubble is a pocket universe, a finite or perhaps infinite region where inflation has ended and normal expansion has taken over. Our observable universe is a tiny patch within one such pocket, perhaps much smaller than the total extent of the pocket. The pocket itself might be infinite if the bubble, once nucleated, expands to infinite size, or it might be finite, but vastly larger than our observable region. Other pockets exist in the eternally inflating space, each separated by regions where inflation continues. The entire structure, the collection of all pockets plus the inflating space between them, is sometimes called the multiverse or the megaverse. This structure has no edge in the usual sense, because the inflating regions grow without bound, continuously creating more space. The multiverse as a whole is eternal into the future, constantly producing new pocket universes, though it may have had a beginning in the finite past, when inflation first started. The string theory landscape introduces another layer of complexity to the multiverse concept. String theory, an attempt to unify quantum mechanics and general relativity by modeling fundamental particles as tiny vibrating strings, predicts the existence of extra spatial dimensions beyond the three we experience. These extra dimensions must be compactified, curled up into tiny shapes too small to detect directly. The way these dimensions are compactified determines the effective laws of physics in the remaining three large dimensions, including the masses of particles, the strengths of forces, and the number of particle species. The string theory landscape refers to the vast number of possible ways to compactify the extra dimensions, estimated to be around 10 to the power of 500 different configurations, each corresponding to a different set of low-energy physics. The connection between the landscape and the multiverse arises when we combine string theory with inflation. If different pocket universes in the inflationary multiverse can have different compactifications of the extra dimensions, then each pocket has different physical laws. One pocket might have strong nuclear forces and weak electromagnetic forces. Another might have different particle masses or even different numbers of fundamental forces. Our universe, with its particular values of physical constants and its specific particle content, would be just one possibility among the 10 to the power of 500 or more, realized in different pockets across the multiverse. This landscape multiverse combines the inflationary mechanism for creating separate spatial regions with the string theory mechanism for varying the laws of physics, producing a multiverse of staggering diversity, where nearly every conceivable set of physical laws is realized somewhere. The anthropic principle becomes relevant when considering a multiverse with varying physical laws. The anthropic principle observes that we can only find ourselves in a universe capable of supporting life, because universes without the right conditions would produce no observers to wonder about them. In a single universe, the anthropic principle is often dismissed as a tautology, an observation that explains nothing. But in a multiverse where different pockets have different physical laws, the anthropic principle becomes a selection effect. Most pockets might be sterile, unable to form stars, or atoms, or any complex structures. Only a small fraction of pockets, those with physical constants in narrow ranges allowing for complexity, would develop life. We necessarily find ourselves in one of these rare, life-permitting pockets, not because our universe is special in any cosmic sense, but because only life-permitting universes produce observers. This transforms the anthropic principle from a tautology to a testable framework for making predictions about what we should observe if the multiverse hypothesis is correct. The fine-tuning problem motivates much of the interest in multiverse theories. Many physical constants appear fine-tuned, meaning small changes in their values would make the universe dramatically different and typically inhospitable to life. If the strong nuclear force were slightly weaker, atomic nuclei could not form. If the electromagnetic force were slightly stronger, stars would burn too quickly for life to evolve. If the cosmological constant were much larger, the universe would have expanded so rapidly that galaxies could never form. These coincidences have puzzled physicists for decades. Why do the constants have values in the narrow ranges that allow for complexity and life? One answer is design, an intelligence that set the constants to permit life. Another answer is pure chance, we got lucky. A third answer is the multiverse combined with the anthropic principle. If all possible values of constants are realized in different pockets, and if we can only exist in pockets with life-permitting values, then the apparent fine-tuning is explained as a selection effect without requiring design or incredible luck. The many-worlds interpretation of quantum mechanics posits a completely different type of multiverse, one arising not from cosmic inflation or varying physical laws, but from the quantum nature of reality itself. In standard quantum mechanics, a particle can exist in a superposition of multiple states simultaneously until measured, at which point the superposition collapses into one definite state. The many-worlds interpretation rejects collapse, proposing instead that all possible outcomes of a quantum measurement actually occur, each in a different branch of reality. When you measure whether an electron is spin-up or spin-down, the universe splits into two branches, one where you measure spin-up and one where you measure spin-down. Both outcomes happen, both versions of you exist, but they inhabit different branches that cannot interact. This branching occurs constantly, with every quantum event, creating an exponentially growing tree of parallel realities. The Everettian multiverse, named after Hugh Everett, who proposed the many-worlds interpretation, is fundamentally different from the inflationary or landscape multiverses. The parallel universes in the many-worlds interpretation are not separated regions of physical space, but rather distinct branches of the quantum wave function of the universe. They all occupy the same space in some sense, but are orthogonal to each other in an abstract mathematical space called Hilbert space. An observer in one branch cannot detect or communicate with observers in other branches because the branches are in quantum states that do not interfere. The many worlds interpretation is controversial among physicists, with strong supporters and strong critics, but it remains a logically consistent interpretation of quantum mechanics and has the attractive feature of being deterministic, with no need for the mysterious collapse process that plagues other interpretations. The number of worlds in the many worlds interpretation is difficult to define precisely. If every quantum event spawns new branches, and if quantum events occur continuously throughout space, then new worlds are being created at an enormous rate, potentially creating an infinite number of worlds in any finite time, if space is infinite, or if quantum events can be divided arbitrarily finely. However, not all physicists who support many worlds believe in an infinite number of worlds. Some argue that only certain special quantum events, involving macroscopic superpositions or measurements by conscious observers, cause genuine branching, limiting the number of worlds to something large but finite. Others argue that the concept of counting worlds is ill-defined because branches can merge or split in complex ways, making it unclear what constitutes a distinct world. Despite these ambiguities, the many worlds interpretation clearly implies some form of multiverse where all quantum possibilities are realized. The observable consequences of the many worlds interpretation are subtle and controversial. In principle, the many worlds interpretation makes the same predictions as standard quantum mechanics for all observable phenomena, which is why it is considered an interpretation rather than a different theory. However, some physicists argue there might be subtle differences in probability predictions or in how we should reason about anthropic questions. For instance, if you are about to perform a quantum experiment with two possible outcomes, standard quantum mechanics gives probabilities for each outcome. But in many worlds, both outcomes definitely occur. How should you think about your subjective probability of experiencing one outcome versus the other, if you will definitely experience both in different branches? This problem of probability in many worlds remains unsolved and contentious, with various proposals for how to recover the standard probability rules from the deterministic branching structure. The mathematical universe hypothesis, proposed by physicist and cosmologist Max Tegmark, takes the multiverse concept to its logical extreme. This hypothesis proposes that every mathematically consistent structure exists physically as a universe. If a set of mathematical equations can be written down consistently, then somewhere in the vast space of possible realities, a universe exists that is described by those equations. Our universe, governed by the laws of physics we have discovered, is just one mathematical structure among infinitely many. Other universes might have different numbers of dimensions, different symmetries, different types of particles, or even different logics. This level 4 multiverse, as Tegmark calls it, encompasses all possible mathematical structures and therefore all possible universes in the broadest conceivable sense. The hypothesis is highly speculative and difficult or impossible to test, but it represents a kind of ultimate multiverse, a Platonic realm where all mathematical possibilities are physically realized. The brane cosmology scenario comes from string theory and M-theory, proposing that our universe is a three-dimensional membrane, or brane, embedded in a higher dimensional space called the bulk. Other branes might exist in the bulk, representing other universes with which we could potentially interact gravitationally, but not through any other forces. The extra dimensions of the bulk could be large, potentially infinite, or they could be compact, curled up on scales anywhere from subatomic to astronomical. In some brane world models, our brane is just one of many, separated by distances in the extra dimensions. These branes would be parallel universes in a literal geometric sense, separated by spatial distance, but in directions we cannot access because we are confined to our three-dimensional brain. Gravity, however, might propagate through the bulk, allowing indirect detection of other brains through their gravitational effects. The ekpyrotic scenario is a specific brain cosmology model proposing that the Big Bang was caused by a collision between brains. In this model, our universe exists on one brain that periodically collides with another brain, and each collision heats the brains and produces the matter and radiation we observe. The ekpyrotic model offers an alternative to inflation for explaining the large-scale properties of the universe, and it naturally includes a multiverse structure with multiple brains representing different universes. The collisions between brains could occur repeatedly, potentially leading to cycles where universes are destroyed and reborn in collisions, creating a cyclic multiverse that oscillates eternally. While the ekpyrotic scenario has attractive features, it faces theoretical challenges and has not gained as much acceptance as inflationary models, but it remains an active area of research in theoretical cosmology. The simulated universe hypothesis proposes that our universe might be a computer simulation created by an advanced civilization in some higher reality. This is a multiverse of sorts because if our universe is a simulation, there could be many other simulated universes running on computers in the base reality, plus the base reality itself. The simulation hypothesis gained attention from philosopher Nick Bostrom's simulation argument, which suggests that if civilizations typically develop the ability to run ancestor simulations and choose to run many such simulations, then most observers who think they are in a base reality are actually in simulations. The hypothesis is unfalsifiable in its strongest form because any evidence we might find for being in a simulation could itself be part of the simulation. But some physicists have proposed ways we might detect signs of simulation, such as unexpected regularities in physical laws that reflect computational shortcuts or limitations in the simulating computer. The cosmological natural selection hypothesis, proposed by physicist Lee Smolin, suggests that universes reproduce through black holes, with each black hole creating a new universe with slightly different physical constants. If universes that produce many black holes have a fitness advantage, creating more offspring universes, and if the constants are slightly mutated during reproduction, then a kind of natural selection occurs at the cosmic level. Our universe, with its particular constants, would be the product of billions of generations of universe reproduction, selected for the ability to produce black holes. This hypothesis predicts that our universe should have constants close to optimal for black hole production, a prediction that can be tested by seeing whether small changes in constants would increase or decrease black hole formation. The hypothesis faces challenges, particularly in explaining the mechanism by which new universes form in black holes, but it represents an interesting attempt to explain fine-tuning through evolutionary principles rather than design or pure chance. The testability of multiverse theories is perhaps the most contentious issue in the debate over whether the multiverse is science or speculation. Critics argue that if other universes are forever beyond our ability to observe, then the multiverse is not a scientific hypothesis, but a metaphysical speculation. Science, they argue, deals with testable predictions about observable phenomena, and if we can never observe other universes, then their existence or non-existence makes no difference to any measurement we can perform. Proponents counter that multiverse theories do make testable predictions, not about the existence of specific other universes, but about the properties of our own universe. For example, the landscape multiverse combined with anthropic reasoning makes statistical predictions about what values we should observe for physical constants if we are typical observers in a multiverse. These predictions can be compared with measurements to test the framework. The collision signatures between bubble universes offer one of the most concrete possibilities for observational evidence of the multiverse. In eternal inflation, bubbles are nucleated throughout the inflating space, and occasionally two bubbles might expand until their boundaries meet. If our bubble collided with another bubble early in our cosmic history, the collision would have left an imprint in the cosmic microwave background radiation, appearing as a circular pattern of temperature fluctuations. Cosmologists have searched for such collision signatures in the data from the Planck satellite and other experiments. So far, no convincing evidence has been found, but these searches place limits on how common collisions are and what properties other bubbles might have. The absence of detected collisions tells us either that collisions are rare, that the signatures are too subtle to detect with current instruments, or that the inflationary multiverse picture is incorrect. The Boltzmann brain problem poses a challenge to certain multiverse models, particularly those with eternal inflation. A Boltzmann brain is a hypothetical self-aware entity that arises spontaneously from random quantum fluctuations in a vast, old universe. In an eternally inflating multiverse that lasts forever, infinitely many Boltzmann brains will eventually form through random fluctuations, vastly outnumbering the brains that form through normal evolutionary processes in galaxies. If most observers in the multiverse are Boltzmann brains with random, unreliable memories and perceptions, then we should expect to be Boltzmann brains ourselves, which would mean our memories and observations are likely false. This leads to a paradox because we used observations to develop the eternal inflation theory in the first place. The Boltzmann brain problem suggests that naive versions of eternal inflation predict we should observe completely different things than what we actually observe, which is a serious difficulty. Various proposals have been made to avoid this problem, such as arguing that certain cutoffs or measures should be applied to count observers. But the problem remains an active area of debate. The measure problem in eternal inflation asks how to assign probabilities to different observations when comparing infinite sets of outcomes. In eternal inflation, every possible event that can occur will occur infinitely many times across the multiverse. If we want to calculate the probability of observing some particular property, like the value of the cosmological constant, we need to define a measure that assigns relative weights to different outcomes, even though each occurs infinitely often. Different choices of measure give different predictions, and there is no consensus on which measure, if any, is correct. This makes it difficult to extract definite predictions from eternal inflation, turning many questions into matters of choosing a measure rather than testing physics. Some physicists view the measure problem as evidence that eternal inflation is incomplete or incorrect, while others see it as a technical challenge that will eventually be solved with better understanding of quantum gravity. The philosophical implications of the multiverse are profound and touch on fundamental questions about existence, explanation, and scientific methodology. If the multiverse exists and all possible universes are realized somewhere, then the question of why our universe has the properties it does receives a new kind of answer. It has these properties because all properties are realized somewhere, and we observe these particular properties because we can only exist in a universe with life-permitting properties. This is a radical departure from traditional scientific explanation, which seeks fundamental reasons why things are as they are. In the multiverse, many facts about our universe have no deeper explanation than observer selection. This troubles some philosophers and scientists who feel it abandons the search for truly fundamental understanding, replacing it with an anthropic shrug. Others embrace the multiverse as a necessary consequence of our best physical theories, arguing that demanding a deeper explanation is like demanding an explanation for why mathematics has the structure it does. The religious and theological responses to the multiverse vary widely. Some religious thinkers see the multiverse as threatening because it potentially eliminates the need for a creator to fine-tune the constants of our universe. If all possible universes exist, fine-tuning is no longer remarkable and requires no explanation beyond statistics and selection. Other religious thinkers embrace the multiverse, arguing that a creator capable of producing an infinite diversity of universes is more impressive than one who produces only a single universe. Some argue that the multiverse actually strengthens arguments for a creator because the existence of all possible mathematical structures or all possible quantum branches seems to require some kind of ultimate ground or explanation, which could be identified with a divine source. The debate continues without resolution, as it involves metaphysical questions that go beyond what physics alone can address. The popular culture portrayal of the multiverse often confuses different types of multiverse theories, blending the many worlds interpretation with the landscape multiverse and various science fiction concepts. Movies and television shows frequently depict parallel universes where different versions of characters live out alternative histories, usually accessible through portals or special devices. While entertaining, these portrayals bear little resemblance to the actual multiverse theories proposed by physicists. The many worlds interpretation does involve parallel realities, but they are not accessible through portals because the branches are quantum, mechanically orthogonal, and cannot interact. The inflationary multiverse involves separate spatial regions, but they are separated by distances or inflating regions that make travel between them impossible, not by thin barriers that can be crossed with the right technology. Nevertheless, popular interest in multiverse concepts reflects genuine curiosity about fundamental questions of existence and possibility, even if the scientific reality is more subtle than the fictional portrayals. The quantum decoherence process is crucial for understanding how branches in the many worlds interpretation become effectively separate. Decoherence occurs when a quantum system interacts with its environment, causing different components of the superposition to become entangled with different environmental states. Once this entanglement is established, the different components no longer interfere quantum mechanically, and they behave as if they are in separate classical worlds. Decoherence happens extremely rapidly for macroscopic systems, typically in timescales far shorter than can be measured. This explains why we never observe macroscopic superpositions in everyday life, even though quantum mechanics says they should exist. In the many worlds interpretation, decoherence is the process that creates new branches or makes existing branches distinct. Understanding decoherence is essential for making the many worlds interpretation precise and for understanding when and how branching occurs. The comparison between multiverse theories and other speculative physics, like supersymmetry or extra dimensions, is instructive. For decades, physicists have explored theoretical ideas that go beyond the established standard model of particle physics, motivated by mathematical elegance, theoretical consistency, or the hope of solving outstanding problems. Many of these ideas, like supersymmetry, made predictions that could be tested at particle accelerators, and when those predictions were not confirmed, confidence in the theories decreased. Multiverse theories are similar in being motivated by theoretical considerations and potential solutions to problems like fine-tuning, but they differ in that direct observational tests are much more difficult. This has led some critics to worry that multiverse theories represent a departure from the traditional standards of empirical science, accepting theoretical speculation as truth without adequate experimental confirmation. Proponents argue that the multiverse may be an inevitable consequence of well-established theories like inflation and quantum mechanics, and that indirect tests, through their predictions about our observable universe, are sufficient to make them scientific. The future observational prospects for testing multiverse theories depend on advances in cosmology, particle physics, and quantum experiments. Better measurements of the cosmic microwave background could potentially reveal subtle patterns, indicating collisions with other bubbles or other anomalies predicted by specific multiverse models. Particle physics experiments might discover evidence for extra dimensions or supersymmetry, lending support to string theory and the landscape multiverse. Quantum experiments might find violations of standard quantum mechanics that favor or disfavor the many worlds interpretation. Improved theoretical understanding might sharpen predictions or find new ways to test multiverse ideas. Alternatively, future work might show that multiverse theories are untenable, either because they lead to contradictions, make predictions inconsistent with observations, or fail to solve the problems they were designed to address. The next few decades of research will be crucial in determining whether the multiverse remains a speculative idea or becomes an accepted part of our scientific worldview. The ethics of research on untestable theories, like the multiverse, raises questions about how scientific resources should be allocated. If the multiverse is untestable, is it worthwhile for physicists to spend time developing multiverse theories and for funding agencies to support such research? Some argue that exploration of fundamental theoretical questions is intrinsically valuable, even if practical applications or experimental tests are distant or impossible. Theoretical work has often led to unexpected insights and applications, and cutting-edge physics has historically pushed into territory where experiments were not immediately feasible. Others argue that without the constraint of empirical testing, theoretical physics risks becoming detached from reality, pursuing mathematical beauty or philosophical speculation rather than genuine understanding of nature. This tension between theoretical exploration and empirical constraint is long-standing in physics, and the multiverse debate is just the latest context in which it arises. The relationship between the multiverse and Occam's razor is paradoxical. Occam's razor suggests we should prefer simpler explanations over complex ones, and at first glance, postulating infinitely many unobservable universes seems like a dramatic violation of simplicity. However, proponents argue that the multiverse is actually simpler than alternatives. Inflation, which predicts the multiverse in its eternal form, is a simple theory with fewer arbitrary elements than the standard Big Bang model. Quantum mechanics without collapse, which gives the many worlds interpretation, is simpler than quantum mechanics with collapse because it eliminates the need for an additional collapse process. String theory, which predicts the landscape multiverse, is simpler in mathematical structure than many other attempted theories of quantum gravity. By this reasoning, the multiverse is not an extra hypothesis added to explain fine-tuning, but a natural consequence of the simplest theories that explain other phenomena. The multiverse emerges automatically from theories chosen for their simplicity and explanatory power, not as an ad hoc addition. The existential implications of living in a multiverse are difficult to fully grasp. If every possible version of events occurs somewhere in the multiverse, then every decision you make differently in some branch. Every possible outcome of every event in your life is realized in some universe or branch. Then questions of choice, responsibility, and meaning take on new dimensions. Does it matter what choices you make if all choices are realized somewhere? Does the existence of versions of you leading radically different lives diminish or enhance the significance of your particular life? These questions have no scientific answers, but touch on deep issues of personal identity and value. Some people find the multiverse empowering, suggesting that human potential is fully realized across all branches, even if limitations exist in any single branch. Others find it disturbing or even nihilistic, suggesting that nothing is unique or special if everything possible happens. These reactions reflect how deeply metaphysical assumptions about uniqueness and significance are embedded in human thinking. The information-theoretic perspective on the multiverse focuses on how information is distributed and processed across different universes or branches. In the many worlds interpretation, information is never lost, but spreads across branches through decoherence. In the inflationary multiverse, information about conditions in one pocket universe cannot reach other pockets, creating information horizons that partition the multiverse into causally isolated regions. The holographic principle suggests that information in any region is encoded on its boundary, which has implications for how we count universes and measure probabilities in the multiverse. Understanding information flow and storage in multiverse scenarios may be crucial for resolving paradoxes like the Boltzmann brain problem, and for understanding how observers should reason about their location in a vast space of possibilities. The landscape of possible universes, whether described by string theory, compactifications, or some other framework, raises the question of whether all possibilities are equally likely, or whether some are preferred for dynamical or statistical reasons. If certain regions of the landscape are easier to reach through the dynamics of cosmic evolution, those universes would be more common in the multiverse, and we would be more likely to find ourselves in one of them. Anthropic reasoning could then be combined with dynamical considerations to make predictions about what we should observe. For example, if universes with certain properties tend to produce more observers, we should expect to find ourselves in such a universe. This combination of dynamics and anthropics is more predictive than pure anthropic reasoning alone, and it represents a way to make the multiverse framework more scientifically rigorous. The ultimate fate of the multiverse depends on which version of the multiverse we consider and what the fundamental laws governing it are. In eternal inflation, the multiverse continues forever, constantly producing new pocket universes as inflation proceeds in the background. In the many worlds interpretation, the branching continues indefinitely as quantum events occur. In cyclic models, the multiverse might oscillate eternally through repeated cycles of destruction and creation. Alternatively, some theories suggest the multiverse itself might have an end, perhaps through some kind of phase transition that affects all pockets or branches simultaneously, or through the gradual decay of unstable quantum states. The far future of the multiverse, like its origin, remains deeply uncertain, depending on physics we do not yet fully understand. Could there be other universes beyond our edge? The honest answer is that we do not know, but theoretical considerations suggest it is plausible and perhaps even likely. Our best theories of cosmology and quantum mechanics, when pushed to their logical conclusions, seem to predict some form of multiverse, whether it is the spatial extension beyond our horizon, the branching of quantum possibilities, or the bubble structure of eternal inflation. These predictions remain speculative and difficult to test directly, but they emerge from theories that successfully explain many other phenomena we can observe. The multiverse is not an arbitrary speculation, but a potential consequence of taking our best physics seriously. Whether these other universes really exist, what properties they have, and whether we will ever find convincing evidence for them, remain among the deepest open questions in science. Questions that challenge our understanding of reality, causation, observation, and the very nature of existence itself, inviting us to expand our conception of what is possible and to confront the limits of human knowledge at the grandest imaginable scales. As we ponder the possibility of other universes beyond our observable edge, we naturally turn to consider what all of this means for our place in the cosmos, for the significance of human existence in a potentially infinite multiverse, and for how we should understand our role as conscious observers capable of contemplating these vast and perhaps ultimately unknowable structures. Will we ever reach or see the true edge of the universe? The answer is both simple and profoundly unsettling. No, we will not. Not because of technological limitations that future generations might overcome. Not because we lack the funding or the will or the ingenuity, but because the laws of physics themselves forbid it. The edge of the observable universe is not a place we could visit if only we had faster spacecraft or better telescopes. It is a horizon defined by the fundamental structure of space-time, by the speed of light, and by the expansion of the universe. Even if we could somehow travel at the speed of light, even if we had infinite time and infinite resources, we could never reach the edge, because the edge is receding from us faster than we can approach it. The expansion of space carries distant regions away, at velocities exceeding light speed, creating an impassable barrier, not of matter or energy, but of geometry itself. What we see when we look toward the edge is not the edge as it is now, but the edge as it was billions of years ago. And what lies at that location now, in the present moment, is forever beyond our reach, forever beyond our knowledge, separated from us by an unbridgeable gulf of expanding space and finite light speed. The speed of light represents the first and most fundamental barrier to reaching the edge. Nothing can travel through space faster than light, according to special relativity. This is not a technological limitation, but a feature of space-time itself. The speed of light is not just the speed at which light happens to travel. It is the maximum speed at which any information or influence can propagate through the universe. Massive objects cannot reach light speed at all, because doing so would require infinite energy. Even light itself, traveling at its maximum speed, cannot outrun the expansion of space. A photon emitted from our location and traveling toward a distant galaxy at the cosmic event horizon will never reach that galaxy, because space between us and the galaxy expands faster than the photon can cross it. The photon makes progress through local space, always traveling at light speed relative to its immediate surroundings. But the cumulative expansion of all the space it must cross carries its destination away faster than it approaches. This is the first reason we can never reach the edge. Even light, the fastest possible traveler, cannot get there. The expansion of space creates velocities that exceed light speed at sufficient distances. The Hubble law states that recession velocity equals distance multiplied by the Hubble constant. The Hubble constant is currently about 70 kilometers per second per megaparsec, meaning that for every megaparsec of distance, about 3.3 million light years, the recession velocity increases by 70 kilometers per second. At a distance of about 14 billion light years, the Hubble radius recession velocity equals the speed of light. Beyond this distance, objects recede faster than light. The edge of the observable universe is at about 46 billion light years in proper distance, far beyond the Hubble radius, meaning objects at the edge are receding from us at more than 3 times the speed of light. No spacecraft, no matter how advanced, can catch up to something receding at 3 times light speed. The expansion ensures that the edge remains forever out of reach, always receding faster than we can approach, always maintaining an unbridgeable gap. The accelerating expansion makes the situation even worse. If the expansion were slowing down due to gravity, then although objects are currently receding faster than light, they might eventually slow enough that we could catch them. But observations show the expansion is accelerating, driven by dark energy. This means distant objects are not only receding faster than light, but are also accelerating away from us, increasing their recession velocity over time. Regions that are currently just beyond our reach are moving even farther beyond our reach with each passing moment. The cosmic event horizon marks the boundary beyond which objects are accelerating away so quickly that even a photon emitted now, traveling forever at light speed, will never reach them. This horizon is currently at a comoving distance of about 16 billion light-years, corresponding to a much larger proper distance. Galaxies beyond this horizon are lost to us forever, unreachable and eventually unobservable, slipping away into a region of space that will never again have causal contact with our own. The proper distance to the edge increases continuously, even though the edge remains at the same comoving coordinate. Comoving coordinates expand with the universe, so an object at rest, with respect to the cosmic expansion, maintains fixed comoving coordinates. The edge of the observable universe, defined by the particle horizon, sits at a fixed comoving coordinate, the maximum distance from which light could have traveled since the Big Bang. But proper distance, the distance you would measure if you could freeze expansion and lay rulers end to end, increases as space expands. Every second, the proper distance to the edge grows by thousands of kilometers. Every day, it grows by hundreds of millions of kilometers. We are not getting closer to the edge. We are falling farther behind, unable to keep pace with the expansion that stretches space faster than we can cross it. Even standing still, we are losing ground, watching the edge recede into unreachability. The travel time to reach even nearby galaxies is prohibitive given current technology. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. At the speed of the Voyager spacecraft, humanity's fastest and most distant probe, traveling at about 17 kilometers per second relative to the Sun, reaching Andromeda would take roughly 44 billion years, longer than the current age of the universe. Even at 1% of light speed, an extraordinary velocity far beyond current capabilities, the journey would take 250 million years. To reach galaxies billions of light-years away, at the edge of the observable universe, would require travel times billions or tens of billions of years long, even at relativistic speeds. And that is assuming the galaxies were not receding from us, which they are. When we account for cosmic expansion, the journey becomes impossible in finite time, because the destination recedes faster than we approach. The energy requirements for relativistic travel are staggering beyond comprehension. Accelerating even a small spacecraft to velocities approaching light speed requires enormous energy. The kinetic energy of an object moving at relativistic speeds grows without bound as velocity approaches light speed, following the formula from special relativity. To accelerate 1 kilogram of matter to 99% of light speed requires about 6 times 10 to the power of 17 joules, roughly the total energy output of the United States for 2 weeks. To accelerate to 99.9% of light speed requires 10 times more energy. To accelerate a spacecraft massive enough to carry humans, equipment, and supplies requires energy outputs comparable to the total power generated by our entire civilization over decades or centuries. No plausible propulsion system, no conceivable energy source can provide this much energy. And even if it could, accelerating and decelerating such a spacecraft without destroying it through G-forces presents additional insurmountable challenges. The time dilation effect means that even if we could travel at relativistic speeds, the journey would take billions of years from Earth's perspective. According to special relativity, time passes more slowly for objects moving at high velocities. A traveler aboard a spacecraft moving at 99.9% of light speed would experience time passing normally, but observers on Earth would see their clocks running slow by a factor of about 22. A journey that takes 1 year for the traveler takes 22 years for Earth. At velocities even closer to light speed, this dilation becomes more extreme. In principle, a traveler could reach distant galaxies within their own lifetime by traveling close enough to light speed, but billions of years would pass on Earth. By the time they reached a galaxy billions of light years away, Earth would be long gone, the Sun dead, and the Milky Way merged with Andromeda into an old, quiescent elliptical galaxy. The traveler could never return to report their findings because the home they left would no longer exist. The observational edge of the universe is defined by the particle horizon, but we cannot observe all the way to this horizon with electromagnetic radiation. The cosmic microwave background radiation forms a wall at the surface of last scattering, the point when the universe became transparent, about 380,000 years after the Big Bang. We cannot see beyond this surface using light because before recombination, the universe was opaque. The surface of last scattering is therefore the ultimate observational edge for electromagnetic astronomy, and it is much closer than the particle horizon in terms of time, though at a similar proper distance due to the expansion that has occurred since. We can see this surface in exquisite detail, measuring tiny temperature fluctuations that reveal the structure of the early universe, but we cannot see beyond it. The true edge, the particle horizon corresponding to light emitted at the moment of the Big Bang, remains hidden behind this glowing wall of ancient photons. The neutrino horizon and gravitational wave horizon extend slightly beyond the photon horizon, offering the possibility of observing earlier moments. Neutrinos interact very weakly with matter and decoupled from the cosmic plasma earlier than photons, about 1 second after the Big Bang. If we could detect the cosmic neutrino background, we could in principle observe the universe as it was at 1 second old. Gravitational waves interact even more weakly and could carry information from even earlier times, potentially from the inflationary epoch itself. However, detecting these signals presents enormous technical challenges. The cosmic neutrino background has never been directly detected because neutrinos interact so weakly that building a detector sensitive enough is beyond current technology. Primordial gravitational waves, if they exist, produce subtle effects on the polarization of the cosmic microwave background, and experiments are searching for these signatures, but detection remains elusive. Even if we succeed in observing with neutrinos and gravitational waves, these windows extend our view only slightly beyond the photon horizon, not all the way to the edge. The quantum gravity epoch represents an absolute limit on observation. In the first moments after the Big Bang, when the universe was younger than the Planck time, about 10 to the power of minus 43 seconds, quantum effects dominated the structure of space-time itself. Classical general relativity breaks down at these scales, and we have no complete theory of quantum gravity to describe what happens. The space-time itself becomes uncertain, fluctuating quantum mechanically, and the concept of a smooth space-time with well-defined light cones and causal structure may not apply. This epoch is sometimes called the Planck epoch, and it represents a fundamental barrier to observation. We cannot see into the Planck epoch with any form of radiation or signal, because the very structure of space-time was quantum and probabilistic. There is no classical trajectory for light or gravitational waves to follow, no well-defined sense in which information could propagate. The Planck epoch is therefore the ultimate edge of observability, not because of technological limitations, but because the question of what happened may not have a definite answer in the classical sense. The future evolution of the observable universe will make the edge harder to see, not easier. As dark energy dominates and the expansion accelerates, more and more galaxies will cross the cosmic event horizon and disappear from view. The observable universe, in terms of which galaxies we can see, will actually shrink over time. Galaxies currently visible will be redshifted into invisibility as they cross the horizon, their light stretched to infinite wavelength. In the far future, trillions of years from now, only the local group of gravitationally bound galaxies will remain visible. Everything else will have receded beyond the horizon into permanent darkness. Future astronomers, if any exist, will have access to far less of the universe than we do today. They will not be able to see the cosmic microwave background because it will have been redshifted into undetectably long wavelengths. They will not see distant galaxies or quasars. They will inhabit an observational universe much smaller and darker than ours, with less evidence about the Big Bang, cosmic expansion, and the history of the cosmos. The edge will be closer but more final, a hard boundary beyond which nothing can ever be seen again. The theoretical possibility of wormholes offers no practical hope for reaching the edge. Wormholes are hypothetical tunnels through space-time connecting distant regions, predicted by general relativity, but never observed, and likely requiring exotic matter with negative energy density to remain stable. Even if wormholes exist and could be stabilized, creating one that connects our location to a distant galaxy at the edge would require manipulating the space-time structure across billions of light years, an impossibility for any conceivable technology. Moreover, a wormhole cannot connect to a region beyond our cosmic event horizon, because that region is causally disconnected from us. No signal, no influence, no manipulation of space-time can reach across the event horizon to establish a connection. Wormholes, if they exist at all, can only connect regions within our causal past and future, not regions that have permanently separated from us due to accelerating expansion. The Alcubierre drive and other speculative faster-than-light propulsion concepts likewise offer no real possibility. The Alcubierre drive is a solution to Einstein's equations, where a spacecraft creates a bubble of contracted space in front and expanded space behind, effectively surfing on a wave of space-time distortion. Within the bubble, the spacecraft remains stationary relative to local space and does not violate the light speed limit. However, the Alcubierre drive requires exotic matter with negative energy density, which may not exist, and the energy requirements are estimated to be equivalent to the mass energy of entire stars or even galaxies. Even if these obstacles could be overcome, the drive cannot exceed the local expansion rate of space at cosmic distances. In regions beyond the Hubble sphere, where space expands faster than light, an Alcubierre bubble would still be carried away by expansion, unable to make progress toward the edge. The drive might allow faster travel within our local region of the universe, but it cannot overcome the fundamental barrier imposed by cosmic expansion. The philosophical acceptance of limits is perhaps the most important aspect of understanding why we cannot reach the edge. Throughout history, humans have pushed beyond boundaries that once seemed absolute. We sailed across oceans, flew through the air, escaped Earth's gravity, and walked on the moon. Each time, technology and ingenuity overcame limits that previous generations thought insurmountable. It is tempting to assume the cosmic edge is just another such limit, waiting to be surpassed by future breakthroughs. But this assumption is wrong. The edge of the observable universe is not like the horizon of Earth's ocean. which recedes as we approach but can eventually be crossed. It is not like the speed of sound, once thought an absolute barrier, but broken by engineering advances. The cosmic edge is a limit imposed by the structure of reality itself, by the geometry of space-time, and the finite speed of causality. No amount of technological progress can change these fundamental facts. We must accept that there are absolute limits to human knowledge and exploration, regions of the universe we can never reach, never observe, never know about except through extrapolation and theory. The psychological impact of unreachability is worth considering. Humans are explorers by nature, driven to see what lies beyond the horizon, to reach new lands, to push into the unknown. The knowledge that vast regions of the universe are forever beyond our reach can feel frustrating or even tragic. The universe contains trillions of galaxies we will never visit, quintillions of planets we will never see, countless phenomena we will never witness. All the galaxies beyond our cosmic event horizon, all the structure and complexity they contain, is lost to us as if it does not exist. This realization can provoke feelings of insignificance and isolation, emphasizing how small and confined we are within the vast cosmos. Yet there is also a strange comfort in knowing there are limits. The observable universe, large as it is finite and comprehensible in principle. We can study it, map it, understand it, without facing an infinite task. The existence of horizons makes the universe knowable in a way an infinite, unbounded cosmos might not be. The scientific legacy of the question extends beyond whether we can physically reach the edge. By studying the edge, by pushing our observations to the farthest reaches of space and time, we learn about the origin, evolution, and fate of the universe. Every observation of a distant galaxy teaches us about cosmic history. Every measurement of the cosmic microwave background refines our understanding of the Big Bang. The edge may be unreachable, but it is not irrelevant. It is where we see the universe in its youth, where we observe the processes that shaped the cosmos, where we test our theories against the most extreme conditions. The James Webb Space Telescope, the most powerful space telescope ever built, is designed to observe the edge, to see the first galaxies, to peer back to within a few 100 million years of the Big Bang. Future telescopes will push even closer to the edge, revealing fainter and more distant objects. While we cannot reach the edge physically, we can observe it ever more clearly, bringing its secrets into focus and using those observations to understand the universe as a whole. The generational perspective matters when thinking about cosmic exploration. Humanity has existed in its modern form for only a few 100,000 years. Recorded history spans only a few thousand years. Space exploration has been possible for only a few decades. When we say we can never reach the edge, we mean never in any human timescale, never within the lifetime of our species, or our planet, or even our sun. But the universe is very young compared to its ultimate lifespan. The current age of the universe is about 13.8 billion years. Stars will continue forming for trillions of years. The universe will exist in some form for an inconceivably long time, perhaps forever. It is conceivable, though highly speculative, that intelligence could survive for such timescales, spreading through the cosmos, evolving into forms we cannot imagine, developing capabilities far beyond our current understanding. Such beings might find ways to observe or interact with regions of space we cannot reach, not by overcoming the fundamental limits, but by existing long enough and spreading far enough that their observable universe encompasses regions ours does not. This is not to say they could reach the true edge if space is infinite, but they could explore vastly more than we can, simply by existing in different places and times. The role of mathematics in understanding the unreachable is central to modern cosmology. We cannot visit the edge, but we can describe it mathematically, calculate its properties, predict what we would see if we could observe it. General relativity provides equations that govern the expansion of space, the motion of light, the curvature of space-time. Solving these equations tells us where the cosmic horizons are, how they evolve, what happens to objects as they approach the edge. Quantum mechanics and quantum field theory tell us about the behavior of particles and fields in the early universe and near horizons. String theory and other approaches to quantum gravity attempt to describe the Planck epoch and the quantum structure of space-time. Through mathematics, we can explore regions we can never physically reach, answering questions about what exists beyond our horizon, even though we can never confirm those answers through direct observation. Mathematics extends the reach of the mind beyond the reach of the body, allowing us to comprehend the incomprehensible and describe the indescribable. The ethical implications of unreachability are subtle, but worth considering. If there are civilizations on planets in galaxies beyond our event horizon, we will never communicate with them, never know they exist, never be able to help or harm them. They exist in a completely separate causal realm, beyond any possible interaction. This raises philosophical questions about moral responsibility and the scope of ethical concern. Do we have obligations to beings we can never affect, and who can never affect us? Most ethical frameworks assume some possibility of interaction, some way in which our actions matter to others. In a universe divided by impassable horizons, these frameworks reach their limits. Similarly, if the many worlds interpretation of quantum mechanics is correct, and every quantum event creates new branches, then there are countless versions of ourselves in other branches, living different lives, making different choices. We cannot interact with these other versions, cannot help them or learn from them. The multiverse, if it exists, is filled with entities beyond our reach, existing but inaccessible, real but unknowable. The documentary evidence of the edge exists in the form of light that has traveled for billions of years to reach us. When we observe a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago. The light from that galaxy is a time capsule, carrying information about the past across the cosmos. The edge of the observable universe is populated by the most distant galaxies we can see. Galaxies as they appeared more than 13 billion years ago, just a few 100 million years after the Big Bang. These galaxies are young, small, actively forming stars, very different from the mature galaxies we see nearby. They are the documentary evidence of cosmic youth, showing us what the early universe looked like. What these galaxies look like today, we can never know, because the light showing their current state will never reach us. They have crossed the event horizon, and their present is forever hidden. But their past is preserved in the light traveling toward us, a permanent record of how they were, even though how they are remains unknowable. The limits of technology constrain our observations, but not our imagination. Current telescopes can observe galaxies formed a few 100 million years after the Big Bang. Future telescopes might push this to 100 million years, or even earlier. But there are fundamental limits imposed by the surface of last scattering, by the quantum gravity epoch, by the finite resolution of any instrument. We can build bigger mirrors, more sensitive detectors, longer observation times, but we cannot observe what is intrinsically unobservable. We can imagine what lies beyond the edge. We can theorize and calculate and model, but we cannot confirm our imaginings through observation. This is not a failure of science, but a feature of reality. Science is built on observation and experiment, on testing theories against empirical evidence. When we reach the edge of what is observable, we reach the edge of what can be scientific in the traditional sense. Beyond lies the realm of speculation, mathematics, philosophy, and imagination, valuable and important, but not subject to empirical test. The contrast between physical limits and imaginative freedom defines our relationship with the edge. We are confined to a small planet, in an ordinary galaxy, in a vast cosmos, unable to travel even to nearby stars within a human lifetime, utterly incapable of reaching the edge of the observable universe. Yet our minds can travel anywhere instantly. We can imagine distant galaxies, visualize the cosmic web, conceive of other universes beyond our own. Imagination is not bound by light speed or cosmic expansion. Thought can traverse distances that light will never cross. This freedom is what makes humans unique among Earth's creatures, the ability to comprehend scales vastly larger and smaller than our immediate experience, to understand our place in a cosmos that dwarfs us beyond measure. The edge of the universe may be unreachable, but it is not unthinkable. We can study it, understand it, appreciate it, even though we will never touch it. The humility required to accept unreachability is perhaps the deepest lesson of modern cosmology. For most of human history, we placed ourselves at the center of creation, believing the universe was made for us, that we occupied a special place. Copernicus showed Earth is not the center of the solar system. Hubble showed the Milky Way is one galaxy among billions. Modern cosmology shows the observable universe is possibly an infinitesimal fraction of the whole, that most of reality is beyond our reach, that we occupy no privileged position. We are observers in a remote corner of an unremarkable galaxy, looking out at a universe vastly larger than we can explore, most of which we will never see. This realization demands humility, an acceptance that we are small, our reach limited, our knowledge incomplete, and forever incomplete. Yet this humility is liberating. It frees us from the burden of thinking we must understand everything, control everything, reach everything. It allows us to appreciate what we can know while accepting what we cannot. The beauty of the edge lies not in reaching it, but in contemplating it. The most distant galaxies visible in deep space images are not just scientific data points, but objects of profound aesthetic and philosophical significance. They are ancient, fragile, glimpsed across billions of years and billions of light years of space. They represent the frontier of human knowledge, the boundary between the known and the unknown. They are beautiful precisely because they are distant, because they challenge us, because they reveal the immensity of the cosmos and the limits of our comprehension. Art and poetry have always been drawn to horizons, to boundaries, to the edges of things. The cosmic edge is the ultimate horizon, the ultimate boundary, and it inspires the same sense of wonder and longing that horizons have always inspired. We may never reach it, but we can contemplate it, appreciate it, be moved by it, and in that contemplation, find meaning. The finality of never is difficult to accept. When we say we will never reach the edge, we mean never in the strongest possible sense. Not never in our lifetimes, but perhaps someday. Not never with current technology, but perhaps with future breakthroughs. But truly never, not in any future, not through any means, not even in principle. The laws of physics forbid it, as absolutely as they forbid traveling backward in time, or creating energy from nothing. This finality is alien to the human experience. In our lives, never often means not now, but maybe later. We learn that persistence pays off, that barriers can be overcome, that the impossible becomes possible with enough effort. But the cosmic edge is different. It is a wall built from the fundamental structure of reality, and no amount of effort will tear it down. Coming to terms with this finality requires a shift in perspective, an acceptance that some questions have no answers we can ever obtain. Some destinations exist that we can never reach. Some knowledge remains forever beyond our grasp. The legacy we leave for future generations is not one of reaching the edge, but of understanding it. We cannot give our descendants the gift of physical exploration to the cosmic boundary, but we can give them knowledge. We can map the observable universe, catalog its galaxies, measure its properties, understand its history. We can develop theories that explain what we see and predict what lies beyond our view. We can build telescopes that future astronomers will use to observe even more distant objects, pushing closer to the edge with each generation. We can preserve the evidence, the data, the images, the measurements, ensuring that future humans, no matter how far removed from our time, can know what we learned. This intellectual legacy is humanity's true exploration of the edge, an exploration not of space, but of understanding. And it is an exploration that can continue indefinitely, even though physical travel cannot. The question of whether we will ever reach or see the true edge of the universe has a clear answer, but that answer does not end our relationship with the edge. We will not reach it, we will not see it in its present state, but we will continue to study it, to wonder about it, to be inspired by it. The edge represents both the extent and the limit of human ambition, the farthest reach of our vision, and the boundary beyond which our vision cannot extend. It reminds us that we are finite beings in an incomprehensibly vast cosmos, that our home is precious and small, that our understanding is partial and will always remain so. These reminders are not reasons for despair, but for appreciation. We can appreciate the universe we can observe, the galaxies we can see, the beauty and complexity visible within our cosmic horizon. We can appreciate the fact that we can ask these questions at all, that we have developed the science and technology to probe the distant cosmos and understand our place within it. As we close this exploration of the edge of the universe, we find ourselves returned to where we began, to the fundamental questions about boundaries, limits, and the nature of reality itself. The edge matters because it defines what we can know and what we cannot, what we can reach and what remains forever beyond our grasp. It challenges us to think clearly about observation and inference, about the difference between what exists and what we can access, about the structure of space-time and the evolution of the cosmos. We have journeyed through questions about what the edge is, what it looked like in the past, what happens there according to physics, whether space ends or expands, and whether other universes lie beyond. Each question has revealed another layer of complexity, another perspective on cosmic boundaries. Now, as we consider whether we will ever reach or see the true edge, we confront the final truth that some things, no matter how much we desire them, remain unreachable. The edge is one of those things. It will always recede before us, always lie beyond the next observation, always represent the boundary between knowledge and mystery. And perhaps that is as it should be. Perhaps the universe needs its mysteries, its unreachable places, its questions without answers. Perhaps we need them too, to remind us that reality is larger than our understanding, that existence extends beyond our experience, that the cosmos holds secrets we will never uncover. In accepting this, in embracing the limits of our knowledge alongside the extent of it, we find a kind of peace, a reconciliation with our place in the universe, small but conscious, limited but curious, finite but capable of contemplating infinity. And as we drift toward rest, these thoughts of cosmic edges and distant horizons can settle in our minds like gentle waves on a shore, each question and answer a rhythm carrying us toward sleep, toward dreams where perhaps, unbound by physics, we might travel to those unreachable places and see for ourselves what lies beyond the edge of everything we know.